He has an interview this morning, but he'll be here later today. He's been with me all year in Boston. You met him at the Giovanni at the workshop. He's here. We're staying together in the hotel. He's going also to the Brazilian Logic event next week. I'm not. I gotta go home, but I'm so excited for this week. It'll be great. It'll be great. It's really good to see you. Let's get all this gear going. Should I test this mic or get a test going maybe? Should I remove it? It's showing up for me. I'm seeing it, so it should. Should I reboot the thing? Because I'm seeing it.
Você não lançou, tá não?
And let me reboot this. Let's reboot this. We got time.
Guilherme, você tá aqui? Tem alguém aqui? Você tá sentado aqui? Tem alguém aqui? Tem alguém aqui?
Não.
There we go.
Agora, assim, o que eu achei ruim aqui, assim, o primeiro parece está foi contraditório, porque ele primeiro mostrou que assim, tinha apresentado uma coisa super técnica de uma forma acessível, e daí quando ele entrou no texto, ele disse, mas precisava de um desenvolvimento formal aqui, precisava de um desenvolvimento formal aqui. Ele elogiou e depois reclamou. Não, assim, eles elogiaram bastante e tal, mas ficou essa coisa contraditória. Eu falei, vou deixar prevalecer o que eles concordaram e o resto, tem coisa que eu acho que tem necessidade de o parecerista reclamou que paradoxos, mas quem que é o cara que é um texto abrangente? Mas daí tem um limite de páginas da enciclopédia.
Como é que é o nome do nosso workshop? Lógica, racionalidade,
That's one thing.
Como é que é o nome do workshop? Racionalidade. Lógica, racionalidade. Não tem lógica. Vou falar.
That's why I'm not so interested. It's not as interesting as machine intelligence, robotic autonomy.
Tá faltando a cadeira? Não, tem
Should we do an audio check? So it's good? It's working? I'm good. All right. Excellent. Good morning.
I will talk like in 3 minutes.
Sure. Yeah. Oh, sure. Yeah, absolutely. So there's one chunk until 10:45, and then there's another one later. That's great. That's great. Oh, I got it. I got the time. Yeah, no problem. Thank you. Some water? That'd be, maybe if I could get some water, that'd be great. Like a bottle of water, that'd be great.
Pisa no negócio aí. Olha, aí eu faço o seguinte, eu vou trocar com alguém que eu não chego lá. Nem tô vendo isso aí. Nem tô te vendo.
Pega umas cadeiras só pra aqui,
That's great. Some new people came in, maybe make sure they get a handout.
Acho que tem umas cadeiras ali que elas têm a... Tem tipo uma mesinha pra botar, não sei se isso... Does anyone still need a handout? Everyone has a handout.
Can I start saying something?
It's up to you guys whenever you want to start. I think, but we're officially.
We said 9:30.
We said 9:30. Let me wait, just in case people show up.
Okay,
Yeah.
let's not waste 5 minutes more for late comers.
Giovanni has an interview on Zoom. He'll be here. He'll be here later in the morning.
Okay.
He has
Is
his,
it down now?
he has an interview. Yeah, right now on Zoom. In Italy, so he's got.
Wow.
Yeah. He's back to the
Okay.
Well, one thing we could do. Now, last night we had a bunch of people who were already here, and we went around. But I see the new faces that didn't come to the event last night.
Yeah.
Would you be willing to, like, those of you who are new, who were not here last night? Would you be willing to stand up and introduce yourself to
Yeah, like
everybody?
for instance, you.
Yeah. Here we go. Here we go. Here we go. Nice.
Hello everyone, I'm Daniel, I'm a former philosophy student. I did an MA on the philosophy of psychology, focused on cognitive science. But then I went into computer science, now I work with AI, and I'm fascinated with the mathematics of AI and how it is possible to learn from data in the physical world.
Can I add something? He went to a company expecting to learn something from AI. He learned nothing from AI. Now he's turning back.
I don't learn from my actual work, I learn from reading on the side.
And for your professors.
And from my professors.
No, that's okay. He was a very bright student. I'm very glad that he's now interested in coming back to the university.
That's great. That's awesome.
Okay, whoever.
Who else was not here last night at the event? Who wants to go? Yeah.
Good morning. My name is Natal Oliveira. I am from PUC, Rio Grande do Sul. My background is actually in law. I work with law, but I was always interested in philosophy. And maybe through philosophy of religion, I got into epistemology and philosophy of science, and I've been trying ever since, trying to wrap my head around how inference to the best explanation fits in the Bayesian scheme of things.
I was there, but I came up late.
Yeah, do it. Go for it. Yeah.
Hello, my name is Stefanis. I'm a medical student back at UFES, and I got interested in. I'm a graduate student. I got interested in Lógica when I did a summer school in the University of Unicamp in Australia, in Lógica. And there I got interested in model logic, where I'm currently working on bisimulations for paraconsistent logic.
Wonderful. So model theory and model logic.
Yes, exactly.
Super. Okay, who else wasn't here last night?
First? Yeah. Okay. Hello, my name is Juliana. I'm teaching mathematics here at Faculdade of Technology, School of Technology. My research is in model logic and paraconsistent logic and probability.
And you are the supervisor of the two guys here.
Oh yes, I'm supervisor of my executive school. Miguel, Miguel and Daniel, that's not
Daniel
here.
August.
Yes.
Hello, my name is Kevin Kolaris. I'm from Germany. I am from Munich. I studied at the LMU, and I came here to do my PhD on the philosophy of Frege, and my question is Frege's relation to meta-theoretical questions in logic.
Great.
Hello everyone, my name is Mateus and I'm a PhD student here in Campinas. I study social epistemology.
Good morning, my name is Emilio Valle. I am a master's student at Federal University of Bahia, and I study the epistemic approach to paraconsistency.
Nice. Who else? Is that it? Oh, there you go.
I was a PhD student under Walter. I studied social choice theory and logic, connection between social choice theory and logic. In my master's, I studied interactive semantics, so I've always been in this intersection between logic and social theory, let's say.
And we very important note that he's a lawyer.
Aha. Those are in high demand now.
I didn't say that, but I'm telling you.
Fantastic. Who else? Anybody else who wasn't around last night that might want to? Yes.
My name is Ulisses. I am a PhD student here under Marcelo's supervisor. I study like an intersection between paraconsistency, belief revision, and abduction.
Excellent.
did okay. You present the introducers? No.
No, go ahead.
I'm just an observer.
No, come on. Come on. Come on. Come on.
I'm Arthur. I'm just an observer here because I did like computer science. I'm a computer scientist. But I have no like formal background of logic or interested. So my friends called me here like, can you come? So yeah, sure. This is interesting. So I came here.
I'm glad you did.
And he works
Excellent.
professionally with large language models.
Oh, excellent. Super.
That says about
Yeah.
so
Excellent.
you're not head of sure, you're on the spot. Put everything on the net.
Is there anybody else? I'm hoping that the people who were here can, of course, introduce themselves to the people who weren't here later today, maybe at the breaks, at lunch. Make sure to introduce yourself. To me, especially, I want to make sure I can talk to everybody. But we have all week, so should we? What do you think? Should we get? Maybe we could. Oh, wait, there's one more person. Okay, wait. Yeah, would you go ahead and introduce yourself?
Yeah, sure. I am Pedro Iago, a PhD student at the Escola Normal Superior in Pisa. And I'm good to add source of knowledge.
Awesome. We got people from all over. That's great.
From Italy, Germany, Peru, Argentina, Colombia. There's some reason Colombia is here. From Colombia. We expected 2 people from Colombia. Angie is there, but there were some more new other Colombian people. They didn't come, right? Yeah. No, I don't think so. So, okay, let's say some words. This is a very nice, I suppose, I hope it's going to be a very nice meeting. It's named officially our workshop on logic, rationality, and probability. It is connected to our FAPESP project. We have, for people that don't know, FAPESP is the São Paulo State financing agency for research and PhD, master, postdoc, and inviting professors. It's a super, very good organization. And we have Marcelo and I and Juliana and other people here. We have a project in FAPESP named the Thematic Project. This Thematic Project, we propose to unite, to put together logic, probability, and rationality. And what's exactly is rationality? Perhaps we don't know yet, but we're sort of constructing the concept, right? Rationality is how people think, how they should think, how they do not think, what mistakes they do, connected to logic, connected to probability, connected to other theories of reasoning. And one of our intentions is to build new reasoning tools, like, for instance, defining or proposing new probability theories based on non-classical logic, non-standard logic, which gives us kind of a new way of regarding probability and logic together. Yesterday, Professor Julie Stern mentioned that, also you mentioned that logic and probability goes in parallel, and they never meet, like in the railway, right? You go together and never meet. So we are crossing the path of the railway. Expect that the train to not derail for that. And then this project, especially here, is being financially supported by Northeastern University in the hands of Professor Fitelson, by his personal funds, by our funds at CLE. So we are trying to make everything nice and good for you, and expecting that you have a very nice stay and we learn a lot together. Okay, thank you.
Sure. Oh, well, it's such a pleasure to be back here. Last year I had such a good time, and when we decided that we would do something different this year, we would fly in some people from other parts of South America and some students and have some additional participants. And I'm really glad that we were able to do that. The reason I'm able to do this is because of these people that I'm showing you here. There's really a remarkable group of administrators that have supported me a lot in weird things that I want to do. Especially now in the United States, it's a very challenging time to be able to try to do something like this. So I'm very privileged to be able to do it, and it's because of these people. I also want to thank my staff. We have the most amazing staff, and some of you who are the students here who've talked to Kiana probably, and they're just amazing. In 2 weeks, they got all the flights booked in all the hotel and everything, and it's kind of amazing. They're remarkable.
Kiana is fantastic.
The best, absolutely the best. So I couldn't do any of the stuff I'm doing without them. Either, of course, I want to thank the local organizers who are here, and for all of your efforts on the ground. I organize a lot of events. I know how difficult it is, so I really appreciate that. And of course, the students. Most importantly, that's why I'm here. That's why I want to do things. I want to do things with students and meet new students and try to maybe, hopefully, inspire some students to do something interesting. I don't know. Okay, so you'll notice, I'm hoping everyone got a handout. There's some new people coming in, so we might want to make sure that they eventually get handouts, if we can do that.
I don't have any else. I'm trying to create some more.
Yeah, so there is a handout. It's 11 pages. It's the story I'm going to tell this whole week, at least until Friday. Now, there's 2 barcodes, okay? The barcode on the left is the handout. So if you want, you can just get an electronic version in the meantime, and you can follow along. Or you can get the PDF. That's the left-hand barcode. The right-hand barcode that you see here takes you to my YouTube channel for my Logic course, where I have 23 lectures. These notes are like a compressed version of the 23 lectures into 5, what I guess are going to be 5 lectures. Let's see how it goes. Lectures 16 to 23 are the part about probability and inductive logic. If you already know truth functional logic, you can skip the first 15 lectures. I'm going to talk about that, though, a little bit at the beginning, because that part's actually very important. So that's basically what's going on. So if you want, and you don't have a handout right now, you can just point your camera at the left-hand barcode, and that will get you to the PDF file, and you can follow along until the handouts come that way. Okay, so originally I was planning to do a series of tutorials on automated theorem proving. Now, I'm still going to do that for people who are interested on Friday afternoon, because there's nothing scheduled on Friday afternoon. Is this right? Is this correct? My understanding of the schedule is there's nothing currently scheduled Friday afternoon. Well, I'm going to add this to the schedule. I'm available all day after lunch until whatever, 5:30 or 6. And for those who are interested, let's come here. I assume the room will still be available. Let's come here, bring your computers. We're going to install some theorem proving software, and we're going to talk about theorem proving on Friday and all afternoon. And I figured that was a better way to do this, because some of the students don't have the background. They may not be interested. And so the story I'm going to tell is going to be of very general interest to everyone here. Okay, this is the story I'm actually going to tell during the week. Friday, if you're interested, come bring your computer. We're going to install software, get you able to work on the problems, and then I'm going to tell a lot of stories about automated reasoning and logic and all that jazz. So that'll be Friday afternoon. It'll be more informal, but that's cool. It'll be like a laboratory. We'll make sure everyone gets their software installed on their computer, and we'll just work on some problems together. And I'll take questions, and I'll explain to you a lot of interesting things about automated. I've been working on automated reasoning for many years, and so I've solved some very interesting problems, including recently with Rodolfo, and he'll talk about that a little bit tomorrow, and then I'll talk again about the problems we worked on Friday. So yeah, automated reasoning Friday afternoon. So for those of you who are thinking that's what's going to happen, it is going to happen on Friday, but not in the meantime. Okay, so I'm gonna start in. So I want to tell, this is my story of inductive logic. It's not really historical so much. It's mostly my story of inductive logic. And of course, it starts with propositional calculus. That's where the story begins, and I mean classical propositional calculus here. Okay, so I'm going to start by talking about that. And, okay, so I'm assuming, who here is familiar with classical propositional calculus? Truth tables. Is there anyone who's not familiar with that? Is there anyone who's not familiar with it? Okay, good. That's great. So we can, this part, I don't have to spend too much time, but there are some things I want to say because it's actually important. Okay, so the way propositional calculus works is you have some things that are called atomic sentences. And I want to spend some time talking about what atomic sentences are, because it's kind of important for what I'm going to talk about later. So the idea behind atomic sentences is that they're supposed to be propositions. They're supposed to express propositions that contain no logical constants, no propositional logical constants. So the logical constants here are just the truth functional connectives. Okay, that's what I'm talking about. Okay, so for instance, I might use an atomic sentence that says something like this. It's Monday, or it's Monday today. Okay, the important thing about that statement is it doesn't contain any of the truth functional connectives. It doesn't contain and, or, not, if, then, nothing like that. But what's going to be really important is atomic sentences can contain other kinds of logical constants. That's fine. Ones that are beyond sentential logic. So for instance, I could introduce an atomic sentence like this, which gets interpreted this way. All ravens are black. Okay, for those of you who are familiar with quantifiers and stuff, I could just say all ravens are black. And it's going to be important that it's okay for atomic sentences to be those kinds of propositions. That's fine. They just can't contain truth functional logical connectives. So what I mean is they're atomic from the point of view of sentence logic. But that doesn't mean they don't contain logical constants. Implicitly, they can be extra systematically interpreted as containing higher order things. First order, even second order logic, whatever you want. You can interpret them however you like. That's going to be important later because when we're doing probability modeling in this framework, we want the probability function to be able to encode these extra systematic relations that aren't in the truth functional structure. This is going to be very important later. Okay, that's a really important thing. So the way I'm going to think about sentential logic is anything goes for the atomic sentences as long as they're logically contingent and they don't contain any truth functional connectives. That's the only constraints on it. But it's okay for them to contain other things. They can even be, in a sense, logically related to other atomic sentences in the extra systematic interpretation. So for instance, I could have 3 atomic sentences. I could have one that I'm interpreting as all ravens are black. Then I can have another interpretation which says that some object that I say sample from the universe is a raven. I'm just using A as the name of that object. And then I can have another one that says A is black. Okay, now what's going to happen in this case is there's going to be a sense in which this conjunction entails. Okay, but this entailment, this is not truth functional entailment. Okay, so I'm not going to write that. I'm only going to use this symbol for truth functional entailment. So I'll just say something like implies. So when I use the word implication, that could be any kind of, it could be a logical, it could even be a conceptual relation, but it'll be some kind of a priori thing. But this I'm going to reserve for tautological entailment in the truth functional language. Does everyone understand what I mean? Okay, that's important. Okay. And the reason that I want to be able to do this is because I want to be able to have probability model. This is now, I'm jumping ahead. We won't get to probability until tomorrow, but I just want to give you a flavor of where we're going. So I want to be able to say things like this. I want that to be able to get an extreme or conditional probability, even though there's no tautological entailment there. So I want the probability function to be able to encode these logical or conceptual implications that go beyond truth functional entailment. Do you understand what I'm doing? This is very important. Okay, this is going to be super important for later. That's a feature of probability calculus. The probability function allows you to encode conceptual and logical relations that go beyond truth functional entailment. Of course, truth functional entailment is going to be baked into the probability calculus, but we'll talk about that later. Okay? Okay, so that's kind of important. Okay, and now I want to talk about the connectives. We have a lot to say about the connectives this week. Rodolfo and I are going to talk more. He's going to talk about and then I'm going to talk more about the connectives on Friday when we do theorem proving. We have a lot to say about the connectives, and I just mean the classical connectives. Okay, but for today, and here's now we're getting to page 2. Page 1, I'm just introducing some terminology, which I'm sure you know. Okay, now page 2 is where things get interesting here. So I want to spend a fair amount of time on this. So if we think about the connectives, so if we think about, say, and, or, and not, okay, these are pretty uncontroversial in the sense that they capture a fragment of natural language pretty well. Okay, so here I'm thinking about the fragment of natural language in English where we have and, or, and not. And now, you might have a worry that there's this thing exclusive or, but that's no problem because we can define that. Okay, so if I wanted to define P exclusive or Q, well, I can just say P or Q, and it's not the case that both P and Q. Okay, so that's not a problem. That's not a limitation of the language. The language is able, I think, to express pretty much everything in natural language we want to say that involve these 3 natural language connectives. So that's not the controversial thing in, it's not a very controversial thing, I think, in, or at least I'm not going to treat it as controversial. However, there is a really serious limitation, of course, here, is that we're dealing with truth functional connectives. And that is a very serious limitation, so I want to spend some time talking about that. I want to talk about truth functionality, and that is a limitation. So here, let me give you some examples. So consider this kind of expression, where P and Q are just any propositions that we can write down in the language. And suppose I want to talk about this, P but Q. Well, I'm going to say that definitely entails or implies P and Q. But the converse is not true. Why isn't the converse true? Here implies, again, it's just a very general notion. It's not tautological entailment. Because obviously there's no tautological
The
entailment.
complication is the but, because you say P and not Q. In English, the grammatical meaning of this but is can vary from language to language.
Yeah, so what do you think, so what I'm saying is there's some additional content. So here's what I would say. This entails P and Q, but it also entails some non-truth functional content, let's call it X. Who can say something about X? Who can tell me about, at least give me a description of some of the non-truth functional content of but?
It may seem that P would imply Q, but surprisingly it does not. It would imply not Q, sorry. But it's surprisingly...
I think that's a little too strong, but it's on the right track. I think you definitely, there's definitely something true in what you said, which is this. Q is surprising in light of P. That's correct. That's definitely part of the non-truth functional content. But in English, okay, this is going to be very important later. Probability calculus is going to allow us to analyze that part of the content. Do you see where we're going? Okay. So I'm going to be using probability not just to generalize like entailment, and so that I can talk about the inductive strength of arguments. That's ultimately what I'm interested in. But I think probability already lets you give something of an explication of the content that goes beyond the truth functional content. Is everyone following what I'm saying? We're going to get to this later. This is jumping way ahead, but what we would say is something like this.
Something I found funny because when you teach this to students on the first semester, you find that no one can figure out that but means and.
And not, yeah.
Oh,
For some reason they have in their mind
Yeah.
that it has a difference because it's a pause on the sentence when they say that.
Yes, that's right. And so what I'm suggesting is P but Q implies P and Q, but it also implies more. This is why the converse doesn't hold. There's more content over and above the truth functional content. And what I'm going to say is part of that content can be represented probabilistically in the following way. This is jumping ahead. But the way we're going to represent this part of this non-truth functional content is this claim. The probability of Q given P, the probability of Q on the supposition that P is true, is less than the unconditional probability of Q. Or if you like, it's less than the probability of Q given non-P. Those are equivalent. Those are going to be equivalent later. We'll see that when we get to probability calculus. So I'm jumping ahead here, but so the theme here is, we start with truth functional logic. We're eventually going to put probabilities on top of that. The probabilities are extremely useful, not just for generalizing tautological entailment, which is one of the main applications we're going to talk about. That's the main one. But also for allowing us to encode things like meaning that's not truth functional, or meaning that's higher order logical, that's beyond the tautological structure. Is everyone following what's happening? Okay, this is really important. And this is part of what I'm going to be proposing. So let me give you another example. P because Q. I claim this also implies P and Q. Does everyone agree with that? Okay, why is that? Well, suppose it's true that P because Q. Well, that means P must be a thing that happened, must be true, because things that are false don't have an explanation because they didn't happen. Okay? So P has to be true in order to be explained. Things that aren't true don't have an explanation. They're false. So if you ask why is P true and P is false, that question has a false presupposition, and so it has no answer. Okay. Then, so suppose P is true, and now I say P because Q. Well, if Q is false, that doesn't explain anything. You can't explain something that happened by appealing to something that did not happen. That would be absurd, okay? So the conjunction follows in this implies sense, okay? Not in a tautological sense, because is not a truth functional connected, but it implies P and Q. But it implies something more. Who can say something about the X factor? There's a lot of content here beyond the truth functional content. What's part of it?
Causality.
Yeah, something like maybe Q.
Causal direction.
Yeah, maybe Q causes P or something like that.
Relevance.
Yeah, Q is positively relevant.
Intention.
What'd you say?
Intention.
Maybe. I mean, I guess it depends on. There are many senses of because, right? So there are many senses of because there are many kinds of explanation, right? So maybe it's a teleological explanation. Maybe it's a physical explanation. Maybe it's a causal explanation. You know, there are many kinds of explanations. So depending on the type of explanation, there'll be additional content X. But one thing that seems generally true is certainly this, at least. And so, again, we have something like this. The probability of P given Q is greater than it is a priori. I haven't told you what these probabilities are yet. That's okay, we're going to get to that when we get to probability calculus and inductive logic. That's where we're going. But does everyone see what I'm doing? This is very important. So probability is not just a tool for assessing the strength of arguments that generalizes entailment. It is that, and we're going to talk a lot about that. That's mostly what I'm going to talk about, actually. But it's also this thing that allows us to encode all kinds of things that are above and beyond the truth functional content of the statements involved, including meaning, maybe even additional logical content that's first order or higher order even. That's all fair game. That can all be encoded in a probability function. So what we're doing here, and this is the little philosophy of science more generally, what we're doing is we're modeling. What we're going to be doing is modeling using probability calculus, using probability models, if you like, more generally. Okay, but we're modeling in general. So even when we're doing truth functional logic, we're modeling. Because science is about modeling, that's always what we're doing. What is modeling? What does it involve? Well, it involves a lot of things. One thing it involves is idealization. So when you study physics, the first thing you learn, generally when I was a boy, the first thing I learned was Newtonian physics. This is a false theory. Why is the first thing you learn a false theory? Why would we teach people a false theory?
It's easier to understand.
It's easy to understand. Why else? Why would you want to learn about the models of Newtonian physics when the theory is false?
Why do you say it's false?
Oh, it's false because, for instance, what it says about the motion of Mercury is just demonstrably false. It was falsified in 1915.
Well, you just told me that there is a truer theory. There is a better theory.
Good. This is good. This is what I want to say. So we're modeling. We're modeling. And so models all involve idealization. They all involve falsehood. All models are false.
They involve, I would say they involve degrees of truthfulness.
Okay, but they're strictly speaking false. All models are false. This is a locution people often use, and I want to agree with that. So what I want to say is, when we're doing science, we're constructing models. And some models are better than others for certain purposes, and some models are worse than others for certain purposes. So for instance...
All models are false, but some of them are useful.
Oh yeah, no, that's right. And so Newtonian mechanics is just fine, say if you're trying to predict where a spaceship is in a certain region of the solar system, if it's not too close to the sun, and it's not moving too fast, and it's not too big, etc., 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 then it's fine. NASA still uses Newton's theory to predict where the astronauts are on most missions, and that's close enough for government work. Okay?
But the thing is, you're speaking about physics. That means that there's going to be error involved. In this case, in mathematics, it can go anywhere.
No, there's still error in mathematics.
Yeah, it is error in mathematics. I know that, but the thing is, if you say it's true, it is true for a certain word.
Okay, so let's just slow down. So we're talking about models. Physics was just an example, but I don't want to talk about that because I want to talk about logic. So let's talk about truth functional logic and its models. I'm thinking of it as a class of models. And in fact, I think of everything as a class of models. We're going to think of probability calculus as a class of models. They're all models. Everything's models. Okay, and so modeling is an art. It's not a mechanical process. Okay? It's an art. It's a science, but it's also an art. And that includes truth functional logic. So let's talk about the conditional. Now I want to talk about the conditional. This is where things get controversial when you take logic versus, okay? I don't think it's controversial at all, so I want to give a different perspective. So we have this. In English, we have the indicative conditional, if P then Q. And I want to say, just like in the case of but and the case of because, this implies the truth functional conditional. Here's a way to see that. Suppose the truth functional conditional is false. Then P is true and Q is false. So if you say if P then Q, you've said something false. I'm just proving the contrapositive here. Does everyone agree with me? If you say if P then Q and it turns out P is true and Q is false, you're wrong. And if you made a bet on that, you would lose the bet. Okay? So, however, it has more meaning. Does anyone want to tell me about the non-truth functional meaning of if then?
Sense of causality.
Yeah, causality.
The other one. When we say if P then Q,
Or it is saying that Q is relevant to Q.
Good, exactly. Again, we have positive relevance. So at least we want to say, again, P is positively relevant. Absolutely, and this is the theme in the notes later. P is positively relevant to Q. In other words, probability of Q given P greater than the probability of Q. Absolutely, I think that's definitely part of the content. Some would argue, this is also part of the content, and we'll talk about this more later. Some would argue that the conditional probability of Q given P should be greater than a half. That the consequence should be more probable than not, given the antecedent. Now, not everyone accepts this, but a lot of people, like Adams and Stalnaker, I'm talking about a long time ago, but I don't think Bob Stalnaker agrees with this now, but they did at one time agree with this. And I'm going to talk about these two things a lot later, because that's going to be how my theory of argument strength works. So what I actually want to say, my view is that the X here is something like this. The argument, P therefore Q, is strong. I think that's the non-truth functional meaning of if P then Q. It means there's a sense in which you're sanctioning an inference of Q from P. Okay, so it's like an inference ticket, but I have a particular theory of what that means about what argument strength is. This is the whole lectures are about trying to define what argument strength is. That's where we're going. The conditional is really important. It's a really important case. It's a very difficult case, and there's a lot to be said about it, and we'll talk more about it. But it's a great illustration of modeling, of what I want to say about modeling. So I want to take a little bit of time, and here I'm on the footnote on page 2. And I want to take a fair amount of time to talk about this. So here's a question. Why is the truth functional conditional defined the way it is? And I'm going to offer a very simple explanation of this, and it's going to tie into the way I think about the philosophy of science and the philosophy of logic, the philosophy of modeling, which is what we're always doing. Okay, so here's a question here, and I have this on the handout, but you'll all remember that the way this is defined is this way. And so here we're now getting into how the models work for truth functional logic. The way the models work is every sentence has a bunch of interpretations. How many? 2 to the n, where n is the number of atomic sentences, so here we have 4. These are interpretations. I'm going to call these possible worlds, because I like that ideology of Stalnaker. I kind of like that, as you'll see later. So those are possible worlds, and in this case there's 4 relevant possible worlds, because the truth values are all that matter for the truth functional conditional. They determine, that's what truth functional means. They determine the truth functional conditional. Now this case is uncontroversial. That's what we were saying. The indicative conditional entails the truth functional conditional. And what that means is that this case is uncontroversial. Or I'm going to take it to be uncontroversial. That if P is true and Q is false, then if P then Q is false. It's these other ones that are controversial. Those are the weird ones. Those are the ones where you say, wait, just because the antecedent is false, all conditionals that have false antecedents are true? That's crazy. I mean, it is. It's just crazy. That's not how the conditional works. In English, now I'm talking about the English conditional. That's how the truth functional conditional works, yeah, by definition. And I'll explain why that is. But that's not how real conditionals work. Okay, I think everyone agrees with this, right? I'm among friends here, because now we're getting into what most people think of as non-classical logic. I don't think of it that way, okay, so this is going to be very important in this first couple lectures. I want to propose a different way of thinking that doesn't revise the underlying logic. I'm going to have probability do all the work that the so-called relevant logicians want the logic to do. I think that's a mistake. Okay, so I'm going to argue that that's not the right way to do it. Okay, but I don't want to jump ahead. So why is the conditional defined this way? Well, there's a very simple explanation. So when we're modeling, how does that work? How does modeling work? Well, there are multiple stages. One, select a class of models. I mean, you have to first pick a class of models that you're going to work with. Otherwise, you don't even know what you're talking about. Modeling requires you to start by specifying a class of models. So in the case of physics, it might be the Newtonian models, or it might be the general relativistic models, or it might be the models in quantum electrodynamics. Depends what system you're interested in. Okay? You select a class of models. And then, what do? You find the best model in that class for present purposes, whatever those modeling purposes are. Now, in physics, for instance, the purposes can be myriad. The purposes might just be predicting, or they might be explaining. Okay, there are many purposes of scientific modeling, okay? And they might involve different kinds of explanations within the explanatory frame. That's fine, okay? So, but first you select a class model. Then you pick the best one among those for the job at hand. So for instance, it's no criticism, really, of Newton's theory that it doesn't, now I'm taking back sort of what I said before, it's no really good criticism of Newton's theory to say that it doesn't do a good job of predicting the motion of Mercury. Why? Because that's not really in the domain of purposes that are suited to that class of models. This is why NASA doesn't use them for that purpose. If they do want to predict the motion of Mercury, they use general relativity or some other more accurate class of models. Okay, so this is just how modeling works, but I want to say it works the same in logic, it works the same in linguistics, it works the same in psychology, it works the same in all of the sciences. We're all just doing science here. We're all just trying to understand the world. And the way we do that is via modeling and explanation, okay? Where all of our explanations are mediated through models. Okay, so now if we apply this here, so let's think about logic. Okay, well, one way we might proceed, the most elementary way to proceed, it's sort of the Newtonian way to proceed in logic, if you will, is to start with the class of truth functional models. That is a choice you can make. That's a perfectly legitimate starting point for your class of models. And it'll be good for some purposes and not good for other purposes, and that's fine. Okay? So suppose we make that choice. Okay, and then what we want to do is, we want to, in this case, pick the best definition of, let's say, this conditional that we're looking for the purposes at hand. And now, all the work's going to be done by specifying the purposes. What's the purpose here of introducing the truth functional conditional? Well, there might be many purposes, but let me give you an account of the purposes that makes total sense and explains why the definition is forced upon you. You have to make this choice, the choice we just made. So here's the idea. Here are some facts about the logic of the indicative conditional that I take to be non-negotiable. And so now, let's say, I'm not going to use the arrow. I'm just going to use a star, an asterisk, because it could be any binary connective, right? I'm just going to focus on the conditional, but you could do this for any binary. You could do it for and. Okay, it doesn't matter. But I'm going to think about the conditional. What matters? What do we want? Things are non-negotiable that we want to get right about the English conditional in a logical context? Here are three. We want this claim to be true. This is just modus ponens. In other words, whatever this star thing is, if it's going to play the logical role of modeling the logic of the English conditional, it better at least get this entailment right. P and P star Q should entail Q tautologically. I take this to be not really negotiable. Here's another thing it should get right. Q and P star Q should not, in general, tautologically entail P. This is sometimes called affirming the consequent, and that should be a fallacy. That should not be valid in general. And finally, third thing that I take to be non-negotiable, P star P should be a tautology. And I guess we could just write that this way. That's usually how it's written, right? Okay. If you agree with me that if you're interested in the logical role of the English conditional, and you've are working within the class of truth functional models. You better get at least these things right. Well, these three things uniquely entail that star equals the arrow. The end. That's why the arrow is defined the way it is. It's not because we think it's a perfect model of the meaning of the English conditional. There's no such thing as a perfect model, period. This is Professor Stern's point. There's no such thing as a perfect model. There are better and worse models for given purposes. There's no such thing as a perfect model. So when you read logic texts, and this infuriates me as a logic teacher, and so my logic text doesn't do this, because I think of it as modeling. But a lot of philosophy texts in logic will have these arguments about, is this the correct, what are you arguing about? It's like arguing, is Newton's theory the perfect model of the universe? No, but who cares? It's perfectly good for predicting where the astronauts are, the end. Okay? It's no criticism of it that's of any interest, that it doesn't predict the motion of Mercury. If you want to do that, pick a different class of models. Do you see what I'm saying? Okay, this is really important. The philosophy of logic, to me, is just part of the philosophy of science, which is part of the philosophy of modeling, because that's how science works. You select a class of models, you find the best explication within that class for the thing you're trying to explicate in that context, the end. That's it. That's how science works. If a better class of models comes along, right, and allows you to do things better, great. That's great. Then you should, okay, then we can talk about that. But it's no criticism of the truth functional conditional that it's not a perfect model of the meaning of the English conditional. This is a category mistake. Okay? It's just like criticizing Newton's theory on the grounds that it doesn't predict the motion of Mercury. It's a category error. That just misunderstands how science works. Is everyone following what I'm saying here? This is super important. Okay. So now in the footnote you'll see I list all 16 of the truth functions, which by the way, the first person to do that was C.S. Peirce, in case you're wondering, in his paper, The Simplest Mathematics. He used a different notation, but he was the first to list out all 16 binary truth functions. So I've listed them all here, and here's a nice exercise. I have 10 exercises in these notes. You'll see exercise sub 1 is in footnote 1. Show that the arrow definition is the unique among the 16 available within the class of models definitions that satisfies these three desiderata. This is not a difficult thing to do. It's a lot of cases, but I recommend this as an exercise. It's fun. Well, let's do a couple cases, just for fun. Let's do a couple cases. So consider the following truth function. It's kind of trivial. I'm calling it T, because it's always true. It's just the constant truth function that returns true no matter what the two arguments are. So I'm saying star is just this thing true in this case. And now let's see how it does on the three desiderata. But let's start with the third desiderata. Well, we should ask, is P star P a logical truth? Of course it is, because everything's a logical truth on this connective. P star Q is a logical truth for every P and Q. You see what I'm doing? Okay. Okay, so yes. There's no and here. Oh, yeah, Q could be not P, it doesn't matter, yeah. That's right, it doesn't really matter. We wouldn't allow that because I'm not allowing it to, but yeah, I see what you're saying. Right, so let's think about 2. Or actually, let's think about 2. And what we want is to argue that Q and P star Q does not generally entail P. Well, this thing's always true. So suppose Q is true. Is it possible for P to be false? Sure it is. You see what I'm saying? Just take this world here. Oh, sorry. Take this. Take this one. Yeah, the third one. In that case, the premises are both true. Well, because the P star Q is always true. And Q is true. But P is false. So that shows that we get this desideratum right. But where this one falls down is on modus ponens. Because, of course, P and P star Q is not going to entail Q, because there are worlds, well, this is always true. There are worlds in which this is true and this is false, right? Namely, this one. Do you see what's happening? Okay. I encourage you, do this argument for all. And what you'll find is for every single one of the 16 except our arrow, there'll be at least one that it gets wrong. Sometimes there'll be 2 out of the 3 it gets wrong. I don't think there's any that get all of them wrong. But anyway, that's an interesting meta theorem in itself. Okay, so this is an exercise I give my students. Okay, and the reason I give this exercise, well, to give them practice on truth functional reasoning, but more importantly, we're modeling. So you can't, in a vacuum, tell me how good is my definition. There's no argument to be had there. Philosophers think they're arguing about something. They're not arguing about anything. You first have to tell me what class of models you're choosing your explanations from, and then what explananda you're interested in explaining. That's it. And once you do that, you realize this definition is inevitable. It's unique among all the possible ones within the class of models you've chosen that gets modus ponens being valid, affirming the consequent being fallacious, and P star P being a logical truth. Does everyone follow what I'm saying? This explains why we define it the way we do, just the way you do in science. Not by showing it's a perfect model, because there are none of those. That's a chimera, it doesn't exist. But by showing it's the best among the available chosen class of models for the purposes at hand. And in this case, if you don't get modus ponens, affirming the consequent, and P arrow P right, then you're definitely wrong about the logic of the English conditional. And so you failed. And this is the only one that does that. All the other ones are strictly worse for the purposes of modeling the English, the logic of the English condition. Do you see what I'm saying? They're all worse. So there's no question of which one's perfect. The only question is which is best within the class of models we've chosen to work in. This is a theme for all the lectures. Okay, this is a thing I'm going to harp on throughout the whole thing. So it's super important that we get it right. Questions? This is a good point to take questions. Yeah.
I have one quick question. If you chose like 3 values semantics, maybe there are more cases that work these 3 conditions.
Yes, that's right. So that's exactly right. So as I say, science is modeling. It starts with a choice of class of models. And so the assessments of the relative goodness or badness of an explanation are all relative to a choice of models. If you expand the class, well, now we have to reassess the question. It's a different question. And all I'm saying here is, there's no meaningful question about the better and worseness of a definition, except relative to a class of chosen models and a chosen purpose of explanation. If you try to answer it in an absolute sense, this is meaningless. This is my point. So you're absolutely right. If we had a larger class of models where we allowed 3 values or 4 values, well, yes. Now we have to reassess and we have to rethink our purposes.
You have to clarify which values are going to be taken as the signature or not. Right?
Well, we have to think about our purposes. I think the thing you want to do when you're modeling is you want to have laser focus on what the purpose of the model is. So for instance, suppose you have an inconsistent database and you're trying to manage such a thing, right? Okay, that's a real problem in computer science that people have talked about. And among other people, Belknap and Dunn came up with a 4-valued logic that seems to do a pretty good job of handling that practical engineering problem of, dealing with, in a deductive way, an inconsistent database. Yes, if that's your purpose, truth functional logic is not going to be very good. We can, of course, agree on that. But the important thing is, it's relative to our purposes. This is the thing I want to emphasize. There's no such thing as one logic or one definition being better than another simplicator. That is not a thing. You have to tell me what your purposes are, and you have to tell me what models, what resources you have available to you. And then we can make comparative claims within that. Do you understand? Does this make sense? That's the point I'm making. Very important meta-philosophical point about how science works. Super important. Okay, is this making sense? Is this making sense? Okay, so here I'm addressing what I call semantic limitations of truth functional logic. Of course there are limitations, just like there are limitations of Newtonian physics. Okay, and that's what I'm addressing here. However, in the context of what we're trying to do, which is explain the logic of the English conditional, If all we have to work with is the truth functional models, this is the only game in town. The end. It's the best. There's no further question of, is it perfect? Nothing's perfect. And also, there's no further question of, is it good relative to some vacuum? No. You have to tell me what your purposes are and what available resources you have. Those are the only evaluations in science that are meaningful, as far as I'm concerned. Everything else is either underdetermined or meaningless. This is really important to get out of the way at the beginning. Okay, so those are truth functional notations, right? Truth functions, that's a little tiny part of English or of any natural language, okay? And there's more content. So for instance, with but, there's at least relevance. With because, there's relevance, right? Negative relevance for but, positive relevance for because. With if then, maybe it's something like the argument should be strong, okay? In a sense that I'm going to describe later. Okay, that's a lot of content that goes beyond the truth functional content. Right. But, fine, that's fine. But within the class of truth functional models, you can still do a lot of explaining. There's a lot of things that can be explained perfectly well, just like within Newtonian physics. There's a lot that can be explained, even though it's false in the grand scheme of things in the sense that when you look at the totality of phenomena in the universe, it's not going to be adequate to all explanatory purposes. Sure, but that's true of every model. It'll be true of the general relativistic models too, because inevitably we'll find anomalies with that, and we'll have a theory that supersedes that. I think this is what you were. This is kind of what you were saying, right? Right, Professor Stern?
Yes.
Yes, excellent.
Can I tell a very short story
Please.
about Professor Newton da Costa?
Mm.
Someone, he went into an argument with a student about exactly that if Newton's theory is true or false. Professor Newton used to say that like diamonds are forever, good theories are forever. And the students kept hammering him, no, Newton's theory is false. And at some point, Professor Newton said, well, let's evacuate the building, because the building is about to collapse.
Right.
And the students said, why? The building is standing here for 20 years. But I know for a fact that the engineer that made the project of this building only knew Newtonian mechanics. He never learned relativity or quantum theory, so the building is about to collapse. Okay, Newton theory is good enough.
Absolutely, and all the bridges, and everything basically that we do, 100%. And so I want to say, and this is very important, I want to say, we need to give the same respect to classical logic. Do you understand what I'm saying? We need to give the same respect to classical logic that we do to Newton's theory. This is very important. And I know I'm speaking not to the choir here, but I think it's a very important point. Yeah.
A quick question. Does this view of science, of modeling, commit us to something like a constructive empiricism? The view of Van Prassen that actually, at the end of the day, all we can ask for in science is empirical adequacy.
No. That's one of the purposes you might be interested. So there are many, as I mentioned, there are many purposes in science. One is prediction, or just sort of saving the phenomena. That's one purpose, but no, science has much deeper purposes, like understanding the world. Okay? Yeah, or explanation. Yeah. No, I think these are all scientific purposes. Empirical adequacy is one among many. And if that's your purpose in the context, well, then that will imply things about which models are best for you among the models you've chosen to work with. That's all I'm saying. You have to first tell me what your purpose is. If it's empirical adequacy, sure. Then maybe Newton's theory is good enough for what you're doing. Okay? If it's empirical adequacy up to a certain tolerance, then maybe Newton's theory is fine. But if it's understanding the world in a deeper sense, or if it's explaining, for instance, why Mercury moves the way it does, it's not going to be up to that task. And in the sense that there'll be a better explanation. Not that there's a perfect, there are no perfect explanations. Okay, let's just forget that. There are better and worse relative to certain purposes given certain resources. So I'm arguing for the sort of general logical form of the claims we make. The form should be, this model is better than this for this scientific purpose among these class of models as choices. That's it. That's what I'm arguing for. And I just think that's true in general, it's true in logic, just as it is in physics. And for that reason, we need to be really respectful of the models and what they are able to do. And I think we need to be maybe charitable, too. Because you might think Newton's theory isn't able to explain something, but maybe you just didn't write down a good enough Newtonian model. Okay, so that's maybe on you. I don't know. Okay, so I've talked about semantic limitations of truth functional logic. And that's interesting, and we'll come back to that later when we have probability calculus on the table and we have the theory on board that we're going to use. But what I'm really interested in is not that. I'm really interested in the logical limitations of truth functional logic. And here I will find many sympathetic listeners, although I'm going to take it a very different direction. But I think you're going to agree with everything I say in this section. Well, maybe not everything, but certainly the first part. So I think there are two kinds of ways in which truth functional logic falls short if what we're doing is evaluating the strength of arguments. So now I'm talking about arguments, not individual sentences and what they mean, but arguments. I think there are two kinds of limitations of truth functional logic. One are what I'm going to call overgeneration cases. Cases in which, according to truth functional logic, the arguments are good, but they ain't good. And here I'll find a lot of sympathetic listeners, I think. I'm going to take it a very different direction, though, than those here, because I want to be maximally charitable to truth functional logic in these lectures. And I also think there are undergeneration cases. I think there are cases in which truth functional logic judges an argument to be invalid, but it's actually a strong argument. Now here, non-classical logicians don't have much to say, I'm afraid, in my experience. They're all looking at substructures of classical logic. I think that... Oh, good. Okay, then you'll like this. Then you'll like this, although I'm going to take it a different way. So let's start with overgeneration. Those are the ones that get most of the press in the so-called non-classical logic literature. So these are cases of overgeneration. Intuitive overgeneration. So let me say what I mean by that. So I'm taking this as kind of data. And what I mean by overgeneration is cases of truth functionally valid arguments that intuitively are not strong arguments. So I'm going to use the word strong for just its intuition, and I'm going to say a lot more about what the explicantum is, what the intuition is. But intuitively, put it this way. If you didn't know very much in the background, so take someone who's pretty ignorant, and you gave them this argument, the premise wouldn't provide any good reason for them to believe the conclusion. That's a rough guide for what I'm interested in. Okay, so these are valid arguments that are not strong intuitively, where strong is this providing some reason to believe for someone who doesn't know, is uncertain about the premises, the conclusions, but are not strong intuitively. And okay, there's two kinds of classic cases. These are usually called the paradoxes of entailment. And a lot of literature exists, as I'm sure you know better than I, because you guys really study non-classical logic, although I've studied a lot, not as much as you guys have. So here are the cases I'm thinking of. Let's start with first this one. P, and these are just atomic sentences right now, therefore either Q or non-Q. Okay, this is valid. Why? Well, there's no possible world in which P is true and this conclusion is false. Why? Because there's no possible world in which the conclusion is false. It's implicator. Does everyone see that? Okay, so there's no possible world in which P is true and Q is false, and Q or not Q is false, because Q or not Q is always true. So therefore, this argument is valid, truth functionally. I'm going to stop saying truth functionally, because when I say valid, I just mean truth functionally in these lectures. Okay, that's all I'm talking about. So valid is a technical term, means tautologically, and there's a tautological entailment. And there is here no possible world in which P is true, but the conclusion is false, because the conclusion can't be false. Everyone on board? Okay. I don't think this is a strong argument. I'm going to give a probabilistic explanation of why it isn't strong later. Okay? But one thing that relevance logicians have said, and there's a really nice recent paper, which you maybe haven't read, but you should, by Sean Standifer, called Variable Sharing as Relevance. Really nice paper. And one thing you'll notice about this argument is the premises and the conclusion don't share any variables. So for instance, let's take an example. Let's just make this concrete. Let's say P is the claim, what is the example? Yes, P is the claim that the moon is made of green cheese. Q is the claim that Santa Claus exists. And intuitively, there's this intuition that the relevance logicians have, that somehow P is, in some sense, irrelevant to either Q or not Q. And the way they tend to explain that, this is oversimplifying a little, is that variables aren't shared. Because what the deductive logician, the only resources the deductive logician has, okay, this is a little digression, kind of important. The only resources the deductive logician has are, in a sense, purely formal relations between the units of analysis, in this case, the propositions. Okay. Here's the thing about argument strength. It's not purely formal. Sorry to break that to you. It's not purely formal. So the very idea that you're going to somehow find a purely formal sense in which this doesn't work, that's going to save classical logic, I just think that's a fool's errand. That's not what you should be doing. So I just think that's the wrong diagnosis. There's no formal diagnosis here that's going to give you, in general, the right explanations. That's my view. So what I'm going to do is offer a different explanation, one using probability. And it's a very simple explanation in this case, which we'll come back to later, but the basic idea is the premise is probabilistically irrelevant to the conclusion. Why? Well, I mean, you already know a priori the conclusion is true if you understand the sentence. You know a priori it's true. So P provides no reason to believe it, but neither does Q. So the idea that somehow this argument's bad, but this argument, oh, this one's okay, that just strikes me as silly. I think that misses the point. Q is no more a reason to believe either Q or not Q than P is, in my view. And I'm going to use probability calculus to explain that. So I don't think variable sharing is the right diagnosis. It's not what's wrong with this argument. What's wrong with this argument is the conclusion is knowable a priori in a way that doesn't require evidence. And therefore, if someone claims to give you evidence for it, they've made a category mistake. That's just not how we know it's true. We know it's true just by competence with the concepts and reflection on what it means. If it is true. Now, of course, we have to be a little careful here, because there might be cases we could instantiate Q in such a way, maybe, that maybe the conclusion isn't true. Okay, I'm not thinking about those cases. I'm thinking about cases where it's clear that the conclusion is true and only true, as Graham Priest might say, and it's uncontroversial and everyone knows it a priori, and that's the cases I'm talking about. Okay? Yeah. Yes, that's right. And so this is good. This is good. I'm glad someone raised that. So an intuitionist will say they don't like this argument. And it's not for relevance reasons. It's not for relevance reasons. Okay, this is good. I'm glad you made this digression. So the intuitionist, and here, if you want a great kind of discussion of this, I recommend Michael Dummett's work. He's done the most on this from the point of view that I'm coming from. And he defends a principle which he calls the fundamental principle. It's kind of an amazing thing. And he has a book about metaphysics where he has a whole chapter called the fundamental principle, right? And the principle is this. An agent S can only know a disjunction, P or Q, and here I'll use lowercase letters because it could be any disjunction, if either they know P or they know Q. This is the epistemological thing underneath intuitionism, according to Dummett, and I agree. This is an absurd principle. This principle is clearly false. What's really cool about Dummett is he has a whole chapter in which he starts the chapter with 5 counterexamples. They're all devastating counterexamples, and then he goes on to defend it anyway. This is an absurd thing. Of course you can know either P or Q without knowing which one. Here's how. And let's just take mathematics, for example. Let's just take mathematics. Suppose, and let's be constructivists, okay? Let's suppose we have a constructivist friend who's given a constructive proof that P. And therefore, even according to Dummett, they know that P. They testify to you reliably that P. That's a way of knowing P, I'm sorry. You can know things by testimony. from people who have constructive proofs. I'm sorry, this is just false. So I reject this epistemology that's underneath intuitionism. I just simply reject it. It's just not true that the only way to know a disjunction is by knowing one of the disjuncts. This is just false. Someone has a constructive proof of P, they testify, either P or Q. That's a perfectly good way of knowing P or Q. Okay, so I just reject this principle. It's a false principle in epistemology, as far as I'm concerned. I don't want to delve into this, but I just think this is false. So what I will say in defense, I mean, I'm not totally against intuitionism in the following sense. I do think there's a kernel of truth to intuitionism, and the kernel of truth is this. If there's a mathematical theorem, and there's a non-constructive proof of it, and there's also a constructive proof, generally the constructive proof will be more informative, and will put you in a better epistemic position than the non-constructive proof. Having said that, I think the non-constructive proof is perfectly knowledge-conferring. It's a perfectly good way to know mathematical truths. So I just reject. I reject the principle. I do agree that a constructive proof would be better. You'd be in a more secure state of knowledge. Yeah, that's right. That's fine. But is it required for knowledge that you have a constructive proof? No, of course not. So a famous example of this, right, is are there numbers x and y such that they're both irrational, but x to the y is rational? And okay, well, I don't know, but yeah, because you think, well, let's see, what about the square root of 2? What about x and y being both the square root of 2? Well, okay, so this thing's either rational or it's irrational. Okay, right? If it's rational, you're done. If it's not, just do this. And you're done, because that's equal to 2. I think that's a perfectly good way of knowing that the answer to this question is yes. Having said that, I also believe that if there is a constructive proof, if someone comes along and determines whether this thing is rational, then you're in a better state of mathematical knowledge and understanding. Oh, did I?
The example is not to work anymore because they had proved it already.
Oh, did they prove it?
Yeah, it is rational.
Oh, okay. Well, then great. That's better for my purposes actually, because that's actually better for my purposes. Because then what I want to say is, now that we know, we are in a better state of knowledge with respect to the original question than we were when we had only the non-constructive proof. Having said that, I still want to say that was a perfectly good way to know. It's just a more secure, a more informative knowledge. So knowledge states can be better than each other, okay? You can know P and be in a more secure state by getting more information about why P is true. Those are compatible, but they're both states of knowing, according to me. So I'm not a constructivist because I do think if constructivism means that it's a necessary condition for even knowing whether, then I reject that. However, I concede that if you did have a constructive proof, you'd be in a better, more informative, and therefore a better state of knowledge. Oh, can we restart? Can we reboot it? Maybe maybe reboot it, and then I'll reboot this. That's fine. That's fine. Because I don't need too much more time for this part of it. Because this is just introductory. I mean, we haven't gotten to probability yet. I'm just trying to lay the groundwork for some background. Yeah. It'd be good if I could go another like 15 minutes. Yeah, and then we can push it to the end. Push questions to the end.
If you have questions about this lecture, you can ask at the end of the next lecture.
Yeah, in fact, we'll have a lot of time for discussion because I want to use mostly the next one just for discussion. I'll introduce a little bit of probability, but there'll be plenty of time for discussion. Sorry about that. I don't know what I did there. Okay, so here, just to come back to where we are in the notes. We're talking about overgeneration cases, and I say the argument from P to either Q or not Q, I think that's not a good argument. So here I agree with the intuitionists, but not for their reasons. I just think P is irrelevant to either Q or not Q. It's not a reason to believe it, because you already know it a priori without evidence, if you understand the meanings of the connectives. Okay, that's my point. So I disagree with the intuitionists about why it's not a good argument, but I agree that it's not a good argument. So we're in agreement on the claim that it's not a good argument. It's the explanation why, and then what to do next. That's where we disagree. I don't think revising deductive logic is the thing to do. I think that's a mistake. It's not necessary. Nothing wrong with classical logic here, in the sense that it's doing its job. If we want a more richer theory that includes when you're in a position to know, or when you have a reason to believe, we need probability. That's what I'm going to argue. And we're going to need probability anyway, so fiddling with the deductive logic just isn't going to help. It's not going to solve the problem anyway. It's just not the right intervention. Okay, so let's see, where am I? Here. Okay, let's see. How are we doing? Oh, let's see, so let me do this. Oh, wait, am I here? Wait, maybe. I see it. It says it's fine here. It says it's fine. You know, I could just use the blackboard. Yeah. Blackboard. Blackboard. Yeah, I don't need it. I can just use the blackboard. Chalk. I have notes, right? So, yeah, forget the computer. Just do this. I'm used to this because this is how I teach. But that's fine. Oh, chalk. I haven't done this in years. This is great. Oh, look at this. Okay, so here's where we are. I agree, and I want to say that this argument is not strong. And what I mean by that is, for someone who's uncertain or in a state of ignorance, P is not any reason to believe either Q or not Q. If you're a competent speaker of the language and you understand truth functional logic and you understand the meanings of the connectives, and this is just a simple empirical thing, okay, I'm not thinking about paradoxical cases. This could get weird, depends what Q is, but I'm just thinking simple empirical claims, okay, because that's the example I'm interested in. You already know this a priori in those cases. This is not a reason to believe. And that's why this argument is not strong. The intuitionist wants to say, no, the reason this isn't a good argument is because this isn't Q. If this had been Q, then it would be a good argument, because then you do know one of the, and I say no, that's just missing the point. I don't think that's right. So I reject the claim that the only way to know a disjunction is by knowing one of its disjuncts. That's false. I agree that if you do know which disjunct is true, you're in a more superior state of knowledge with respect to the disjunction than if you don't. Yes, but you could know without that. So I just think Dummett's principle is false. Okay, now the way I'm going to explain this is this way. P is irrelevant in the appropriate sense to Q or not. But I want to say, so is Q. It doesn't matter. That doesn't help. That's not the right intervention. Okay, that's what I'm gonna argue. So here I disagree with the intuitionist. The intuitionist is okay at this point, but here they're going to disagree. And I'm going to say no, they're wrong too. This isn't a strong argument either. Putting Q here doesn't help. That's still a weak argument. Okay, so we'll get to why I think that and how I explain that later. Okay, here's another example, and this one's a little harder and a little bit more tricky, and that's this. P and not P, therefore Q. Now, you guys will love this one. Okay, this is your favorite one. This is your favorite paradox of intelligence here in Brazil. This one is trickier. This one's trickier, but I want to agree and say that this is not a strong argument in general. And so I would say, in other words, if you want to know whether Q, and you're in a state of uncertainty, if someone tells you both P and not P, that's not a reason. That's not a reason to believe Q. Yeah, I just think. Okay, and I'm going to explain that with probability. Okay? Or I'm going to try to. I'm going to do my best to try to explain that with probability. It's a little tricky, but we'll come back to that one. Okay, so these are cases of overdetermination, overgeneration, where The classical logic says they're valid, but okay, they're valid, but they're not good. They're not good arguments. They don't provide reason for an uncertain agent to do something. And I agree with that. I'm just going to use probability calculus to explain this away and explain all the other strong arguments as well. So I'm going to provide a unified general theory of strong argument that explains these and all the other cases that deductive logic couldn't possibly explain because they're not deductive arguments. So I'm going to provide a strictly more general theory and unification of all this stuff. Okay, but before I do that, there's one more thing. And this is a little different than classical, let's call it classical non-classical logic, if you will. Classical non-classical logic doesn't really talk about under-generation cases. This is really not on the agenda for most non-classical logic texts or courses. For instance, Grand Prix texts on non-classical logic. You won't find this in there at all. But I think these are equally important cases. So here's what I have in mind. So let B be the atomic sentence, John is a bachelor. And let M be the atomic sentence that John is married. And now consider the following argument. B, therefore, it is not the case that M. This is not valid, truth functionally. But it's a really good argument. Why isn't it valid? Well, I mean, these are just atomic sentences. So just make B true and M true, and you're done. So it's not a tautological intent, so it's not valid in the logical, in the truth functional sense. It's a good argument, though. This argument, I want to say, is strong. And I'm going to give a perfectly good probabilistic explication of that later. So this is a case where classical logic undergenerates. It says the argument's no good, but it is good. This is a very different kind of case. It's not one that classical, non-classical logic talks about. You won't find it in Grand Prix' book at all. Now I have a footnote here because I want to forestall an objection here that's not going to be helpful. You might say, well, wait, what if I can give a conceptual analysis of bachelor where unmarried is a conjunct? And then that will reveal that this does have a valid truth functional form. It's just hidden the way I've symbolized it here. This is a bad objection because that won't work for all cases. Some concepts do not admit of such a conjunctive conceptual analysis. Which would be required to unpack this in a truth functionally valid way. Even if bachelor does, and I'll give you that bachelor does, I don't really care. There are certainly concepts, I would argue, that do not have such a conceptual. Here's an example. So here's another. Let K be the claim that John knows that it's raining. And let R be the claim that it's raining. And consider the argument K, therefore R. That is not truth functionally valid. No conceptual analysis will help because there is no conjunctive conceptual analysis of knowledge, I claim. And if you want an argument for that, you can read Tim Williamson's book. It's cited in here. Williamson's book, Knowledge and Its Limits, gives a very compelling argument against any conjunctive conceptual analysis of knowledge. And so this just isn't going to work. I claim this is a strong argument. And I also claim with Williamson that no valid truth functional reconstruction of the argument is coming. So you can see, this was just an example. Fine, you can deal with this example. There are going to be things that don't have conjunctive conceptual analysis. If you don't like knowledge, we can come up with some. I just need one case. This is a counterexample. That's how counterexamples work. I only need the one. So you pick your favorite thing that doesn't have a conjunctive conceptual analysis. If you don't like knowledge, pick another thing. You're going to find something out there in science that doesn't have any conjunctive conceptual analysis that would allow you to, quote unquote, unpack this as a conjunction elimination.
You're not doing modal logic in here, right? Only propositional logic.
Propositional logic. Yeah, that's right. I don't think modal logic will help here either, but that's okay. We could talk about that later, but I don't think that's going to help. So what I'm saying is, there's always going to be under-generation cases. And I think this is even true in any formal logic. I don't think it matters. You could, if you had second-order logic, there'd still be under-generation. There'd still be under-generation, I believe. Now, we'd have to have a longer discussion to support that, but I don't think any of those sophistications are relevant. Because again, I think it's the wrong intervention. That's the wrong intervention. The problem here is not with the deductive structure. The problem here is that what we're trying to explicate is some things being a reason to believe another thing when you're in a certain kind of state of uncertainty about the truth of the relevant matters. Deductive logic is just not suited to that task. So I don't think fiddling with the deductive logic is the right intervention. It will eventually fail. It might work on some cases, but eventually it will fail. And you'll need probability or some other more sophisticated framework. You're just going to need that. Okay, so I'm going to stop there. Maybe we can take a few questions if you want, and then we'll take a break, and then I was going to come back and we'll start to talk about probability, because I haven't talked about that. But the purpose of this lecture was really to orient things philosophically in terms of how I'm approaching the whole subject, what I think the underlying principles that govern what we're doing are, and then what some of the problems I'm seeing are, and then later we'll talk about how I think you should solve them, what the right intervention is. Is this making sense? I hope this is making some sense. All right, questions? Maybe for a couple minutes?
About 3 minutes, so maybe one or two questions. You can ask now.
So I have a question about the principle of intuitive logic that you presented us.
Yeah.
So, for example, I imagine a scenario where, like, civil engineer, he wants to know whether 2 columns have been built, which is part of the building. But how can you really, for sure, know that if he hasn't checked this himself? Because he can infer that by seeing that the building has not been built before. He actually going there and looking at the 2 columns and Q and Q, like Q and Q. Column 1 has been built and column 2 has been built. Right? So that's a case where intuitive logic is really good, like you construct it by seeing the column.
Yes,
It's kind of an example.
Well, yeah, I mean, as I said, I agree with the claim that when you do have a certain kind of constructive understanding, that puts you in a better epistemic position. All I'm saying is you can also know, if we're just talking about knowing, you can know things without constructive argument. For instance, testimony from an expert who does have constructive understanding and is very reliable in his testimony. This is a perfectly good way of knowing. If it isn't, then we don't really have any knowledge, because let's face it, people, most of what we know by testimony. So if you're going to reject that, I just think then you're a skeptic, basically. Then you just think you don't know anything.
That's the good way of understanding authority, principle of authority. By listening to a scientist or to Einstein or...
Yes, we have to be able to know things by testimony, because that's how we learn most things, from our peers and from our friends. That's how we know things. You don't want to say that the only way to know something is by verifying it yourself, because no one can do that. For most of scientific knowledge, this is impossible. So that will lead you to skepticism. And we don't want to be skeptics here, so I want to be very clear. I think we have a lot of scientific knowledge. A lot of scientific. I'm an anti-skeptic. I'm like Williamson. I think there's a lot of knowledge. But it's not all by observation, and it's not all by constructive proof. There are many paths to knowledge, including testimony. And I think if you reject that, you're just going to end up being a skeptic at the end of the day. Yeah. No, and that's fine if you want to be a skeptic, but I'm assuming we know a lot of stuff. Yeah. Question? Oh, are we done? We can take questions or we could take at the beginning a couple questions too. Let's do that. Let's take a break, and we'll take a couple questions at the beginning, because this isn't, it's not going to take all 5 lectures. Oh, yes.
Thank you.
The blackboard's better.
Yes, I was thinking about suggesting that too.
Thank you. I normally just use my time.
how would you argue that your theory on what is the best scientific theory, which is that the theory which fulfills the designated purpose in the best way, how do you argue that this is the best theory to model scientific?
Well, I'm open to alternative ways of modeling, of course, the scientific enterprise. I'm open to that, and that should be an open discussion that we have. You know, we should think about that. What are the best ways to model the scientific enterprise? And I'm putting something forward as a possible way of modeling. I'm open to there being better models for various purposes. Now, it depends what we're trying to understand about science, of course. Science is such a diverse and vast subject that it's hard to unify it into any given purpose, or, you know. So I think of it as a more local enterprise. So think of the person who designed and built this building, or the engineer who designed the building. They had certain purposes in mind that were pretty specific, and certain requirements, and the models they were using were adequate to the task. Using general relativity or something just would have been superfluous. It's not helpful. I mean, that just strikes me as intuitively obvious. If you have some examples in mind where you think my way of thinking about it is inadequate, I would like to hear those. But in the absence of a particular case, it's hard to judge. But I'm open to there being counterexamples to my way of thinking, of course. Does that help? Yeah. It's nice to have examples like this.
No, it's just to, my question was how you would, is there a problem with circularity? That you say that your theory fulfills the purpose in the best way?
Well, we're just doing the best we can, and I think we have to take it on a case-by-case basis. So, the engineer, then there's the people trying at NASA, they have their purposes. There's the, people who are trying to predict the motion of Mercury, they have their purposes. And I think we have to take it on a case-by-case basis. But if you have a historical case in mind that doesn't seem to fit my mold, I'd love to hear that.
Okay.
Yeah.
Okay, so now,
Sorry.
I'm interested in constructive mathematics.
Yeah.
And I'd like to make an objection to the two arguments you offered that P cannot be an argument for P over Q. The first argument...
No, P can be an argument for, P is certainly an argument for P or Q. What I claimed was nothing is a good argument for either P or not P.
Well, that can be the case as well in this discussion. So the first argument you made was based on testimony, which is that we can learn a disjunction without knowing whether P or not P. And that's fine, but it's parasitary on the constructive knowledge of someone else. So I want to focus on base knowledge without testimony. And then the argument you gave, one argument you gave was based on rational or irrational numbers, and you assumed that every number was either rational or irrational, which is something that a constructivist could claim is false unless you prove otherwise.
Well, they're not denying, I don't actually think they're denying that. What they're denying is that they're in a position to know that currently. I don't think they're actually denying that that's true. So when intuitionists talk about it, they're not really talking about truth. They're talking about what's constructively provable. And I'm fine with that. I love constructive proof. And if you want to talk about, I'll talk about that all day. I love it. In fact, for Friday, that's what we're going to talk about. We're talking about theory. I love that stuff. And I do think it's better to have a constructive proof generally than a non-constructive proof. I agree with all that. But I do think there are some cases in which having a non-constructive proof is sufficient for knowing the answer. And that's all I want to say. There are some cases. And so therefore, the general prohibition that the intuitionist wants isn't true.
Yeah, there are some cases.
That's all I want. That's all I want to say.
Maybe not all of them. Maybe mathematics is constructive, but other areas of knowledge is not.
That's right. Maybe. And I'm open to that. But I think even in mathematics, there are some cases in which you can know things with non-constructive arguments. Having said that, I do also want to say you're in a better position. You're in a better epistemic position when you have a constructive proof. Those are compatible. Similarly, if you get testimony from a reliable witness, that's a way of knowing. But if you see it yourself, you're in a better position. That's fine. Totally fine. They're both cases of knowing. One's a more secure, more informative way of knowing. No problem. That's what I would say. So I agree with the spirit of it, that constructive arguments are more informative. I agree with that. But that doesn't mean they're always required for knowing.
There's one. Can I ask just a follow-up?
Yeah.
Maybe there are some cases in which P is a strong argument for P or not P, in cases where constructivism is true.
Yeah, I wouldn't want to say that because I just think if you understand what the connectives mean, you already know a priori that either P or not P. So I just think that's how knowledge works. So I wouldn't want to say that, but I would also be willing to say that if you do know which is the case, you're in a better position.
So you're assuming the classical connective.
Yeah, I don't think there's anything wrong with that at all. I don't see a problem with that. And having said that, I agree that you're in a better epistemic position if you know which. Absolutely. So if Dummett had said, look, it's possible to know sometimes the disjunction without knowing it, but if you do know the disjunct, then you're in a better position. I would totally agree with that. If that were the fundamental principle, it's true. He just makes it much stronger than it should be. And he gives 5 counterexamples. Let me just make one comment about this base knowledge. I'm not sure I understand what that means. It's very hard to distinguish what we know based on testimony from what we know in some other way. After all, how did we learn language in the first place? How do we learn mathematical language? I mean, you don't just think about it. It doesn't work that way. You have to talk to other people. Yeah. So I'm not sure there's such a clean distinction there. For me, I'm more of a holist about knowledge. I don't think there's a really good, clean distinction between base knowledge and testimony knowledge. It's all just knowledge. So I take knowledge as kind of primitive. I'm with Williamson on that. I just think knowledge is the fundamental thing in epistemology, and we can't really analyze it, and you have to just take it case by case. And yeah, that's how I think about it. But thank you, those are great questions. Let's keep going. Let's keep going.
We can.
No, let's keep going. Let's keep going.
No, like Mike, then Emily,
yeah.
Then.
Okay, then we'll call.
Then we.
For now, and then at the end.
Yeah.
Good.
So Mike, you can go first.
So when we talk about theories and models and how we compare them, you said that we cannot have a standard way for every theory and every model in general. We always have to work within that nice framework. We want this thing, we want these properties, and within these requirements we can compare.
Right.
Okay. I was thinking, can we model these arguments in a topological way, like a mental, where locally we have structures that allow us to compare theories and models, but globally not necessarily we have.
Yeah. I think that's a good way of modeling that. I like that. I think that's a good mathematical model metaphor for the way I'm thinking about things. I think of things as fundamentally local. You got to tell me what resources do you have, what problems are you trying to solve, what purposes do you have, and then we can evaluate among those resources which one's doing a better job of achieving those goals. So I view it as a very local matter. I don't really understand the global questions. I don't really know what those. I find it very difficult to understand global questions about science. I just don't really have a grip on it. So for me, it's got to be really case by case, what your resources are, what you're trying to do, and then comparing among the different possible models within those resources, which is better for the purpose at hand. That's the only way I know how to evaluate anything. I don't know how to back away and look at something globally. I'm not sure what that means. I kind of lose my grip. So I like that metaphor. It's a good metaphor.
But my question is, can it be more than a metaphor? Could it be really a formal way to model what you are saying to us?
Yeah, depending on what your purposes are, that could be a nice mathematical framework or classic models for modeling a distinction. Sure, it's going to depend on what your purposes are. But yeah.
Okay, so Emily?
My question is, would you say the expert that gives you the testimony must have constructed for it to be considered knowledge?
Right, so this gets back to this question of whether there's like a really principal distinction between base knowledge, whatever that is, and just knowledge that we have in some way or other. I don't really understand that, because then if you say, okay, that's a requirement, well then you have to go back to the expert, and you have to ask, okay, well what's the story of how they came to know? And part of that story is going to be a lot of testimony about how mathematics works, about how logic works, about how language works. That's just how we know everything. So I'm not sure that I even understand the distinction. I think there's things we know and there's things we don't know. And I don't think there's a general theory of knowing. I think we just have to take it on a case-by-case basis. But in my experience, all knowledge traces back to things like testimony, at least in my case. I don't think I would know anything at all if it wasn't for the testimony of my teachers and my peers. That's my view. So I don't know if there's any such thing as just knowing. I don't know what in a vacuum. I don't understand what that is.
Quick question about the undergeneration case.
No, it's you, and then we'll take questions after at the end. Yeah, you're the last one.
Generation cases, for instance, we always try to typically teach them like a memorization problem. For instance, in bachelor example, we all know that bachelor people underneath it's not married. So when choosing models, we always have kind of trade-offs, and the city is one of these qualities we have.
That's right.
So this ad hoc adjustment, isn't that better than a whole new model just to capture these?
Good, yes. These are exactly the kinds of questions we have to grapple with when we're deciding what's the best way to proceed. What I'm going to suggest is that probability calculus is just going to do a better and more direct job of explaining what's going on in these cases and why intuitively these arguments are strong when they're strong and weak when they're weak. But, okay, that has to be judged. You have to look at alternatives and see whether, in fact, I am offering a better explanation. So that's what it'll come down to. Yes, and there'll always be multiple strategies, as Walter mentioned. You could add like a knowledge operator to the logic or something, and then just have an axiom of activity, or so like the T axiom or something. And you could think that's the way to capture that. Yes, you can do that. I don't think that's, in the general, going to be the best way to handle things. I think there's a much more elegant and general way, if what you're interested in. So it all depends on my assumption that what I'm trying to understand is when, for someone in a state of uncertainty, one proposition constitutes a reason to believe another one. That's what I'm interested in. Now, you may not be interested in that. Maybe you're just interested in some platonic thing about following from, or whatever that is, if I understood what that was. That's fine, if that's what you're interested in. So again, it depends on your purposes. But for me, there's this thing, when is something a reason to believe? And that's what I think is behind a lot of the intuitions about strong and weak arguments. We're actually going to get later at the end of the lectures into examples from cognitive science, so-called reasoning fallacies. And I think it's clear that you need probability models there to explain what's going on. Logic isn't going to. It's just the wrong intervention. So that might work. You know, this is sort of fiddling with the structure might work in some cases, and maybe that is best in some cases. But we have to kind of take it on, I think, on a case-by-case basis. But if what you're interested in is, when is this proposition a reason for someone who's in a state of uncertainty to believe another proposition? I just think you need probability to understand that. Logic isn't going to. In general, it might help you in some cases, but it's not going to do all the explaining. That's my opinion. So it's relative to that purpose, right? I hope that's helpful. All right, should we continue? Let's continue. Okay, so now we're on to part 2, the probability calculus, and I'm going to give an algebraic approach. But let me talk a little bit about probability first, just in general. So probability is a really weird thing because, you know, some form of deductive reasoning has been around for a very long time. Aristotle talks a lot about deduction. And, you know, ampliative or non-deductive, or what I'm just going to call inductive. So when I use the word inductive, I just mean non-deductive inference. Okay, so it's just a very broad category. Okay. That kind of inference, those ampliative, non-deductive inferences, they haven't actually been, it hasn't been that long since we've had good models for formalizing and understanding what's going on there. So probability calculus really didn't appear until late 19th, early 20th century in anything like the form we know now. Normally, Kolmogorov is someone who's very important in this connection, and there were people before him, of course. There was W.E. Johnson, who was John Maynard Keynes' teacher, and also the teacher of Frank Renzi, who did a lot of work on probability. There was John Maynard Keynes himself, who wrote a treatise on probability in the 20s before this. But Kolmogorov really, I think, that treatise there in 1933 is probably deserves to be called, like, that was really the watershed. And what he does, which is different than what I'm going to do, is he provides axioms for probability. I'm not, on Friday we're going to talk all about axiomatic stuff because theorem proving is all about proof theory, and I love proof theory, as you'll see on Friday, but I don't think it's the best way to understand initially or to teach probability. Why is that? Well, axiomatic proofs are really hard and weird, and they're not very explanatory about what's going on, especially in the probabilistic realm. But let's just write down a few axioms. So what we're going to have is now we're going to add to our truth tables, we're going to add another column to the truth table. And the column is going to be these, I'm calling them little a sub I. They're real numbers between 0 and 1. Assigned to each of the possible worlds, or each of the states, or the state descriptions. And you can think of those as how probable it is that that world is the actual world. Okay, you can think of it that way. That's how I'm going to think about it. But the way Kolmogorov thinks about it is different. Kolmogorov gives you axioms for a function, and it's a function from this Boolean algebra that we have. That's just this truth functional structure to the unit interval. And it satisfies certain axioms. And I'm going to present these axioms logically. He does it set theoretically, but this is logic, so I'm not going to do that. Okay, I'm just going to do it in terms of logic. And the axioms he gives are these. There aren't any negative probabilities. I mean, that's already a limitation for those of you who are familiar with quantum mechanical probabilities. But let's not. These are models. It's a class of models that we're going to describe, okay? The probability of a tautology is 1. So if T, that's just an arbitrary tautology of the language. Q or not Q if you want, whatever, doesn't matter. They're all equivalent anyway. And then if X entails not Y, that is, if X and Y are inconsistent, then the probability of the disjunction is just the sum of the probabilities of the disjunction. This is called additivity. That's the most important axiom, really. The other two are just kind of arbitrary. It's like a choice of scale, really, for these. This one is the interesting one. That's called additivity. Anyway, he gives these 3 axioms, and those axioms are really taken to characterize probability, unconditional probability. So this is an unconditional probability. Takes a proposition and then in a Boolean algebra and then, or a sentence. Okay, let's just think of it as sentences. Okay, and they satisfy these. Okay. It follows from lots of things follow from the axioms. One thing that follows is this: if P entails Q, then the I'll look at proofs of these that are algebraic later that are very much simpler to understand. The probability of P is less than or equal to the probability of Q, and it follows from that if P is equivalent to Q, then they always have the same probability if they're tautologically equivalent. Okay. So remember, this is tautological down in algebra. So there's lots of things that follow from this, and this is just taken to be sort of the canonical axioms for unconditional probability. Okay, then conditional probability. And okay, this is a little trickier, but the way we're going to talk about this is we're only dealing with finite Boolean algebras here. I have a footnote here about that. As Professor Stern was telling us yesterday, and it's very important, if you have an infinite algebra, there are going to be lots of contingent events that are probably 0. And so but let's set that aside, because I'm just not going to be talking about those cases. Again, we have a class of models. It's suited to certain purposes. That's outside the scope. Just like the motion of Mercury is outside the scope of Newton's theory. And that's okay, because we're just going to talk about this class of models. So what we're going to do is we're going to define the probability of P given Q as a ratio of unconditional probabilities. This is how Kolmogorov does it. So this is just a definition. And okay, one thing to notice about Kolmogorov's theory, and then I'm going to switch to an algebraic way of thinking about this, which is completely different, but it will be equivalent to this theory. One thing that's really important to notice here is that everything supervenes on the unconditional probabilities. Once you have an unconditional probability distribution over the algebra, it determines all the probabilities, because these are just unconditional probabilities here. Okay, and important caveat. Of course, the probability of Q has to be greater than 0. So, and I'm going to talk more about that later, but that's an important caveat, because otherwise the ratio for standard real numbers is undefined. Okay, so that'll just be an undefined conditional probability. This is Kolmogorov's way of doing it. I don't like doing it this way because in order to explain why something's a theorem, you got to do some weird axiomatic proof, which is just not illuminating to me. It could be very complicated. So I actually don't. It's fine. This is the theory. This is one way to specify the class of models I have in mind. But I'm going to do it algebraically, so just talk about the models themselves. I'm not going to talk about the axioms. Yeah.
Professor, must we independently define the probability, the joint probability of P and Q, or does it somehow follow?
It follows.
From
Yeah.
P,
Yeah, it
and Q
follows.
themselves?
Yep, it's going to follow. So let's now get rid of this way axiomatic way of thinking, and I'm going to give you a more perspicuous algebraic way of thinking about classic models. And it'll also be nice because it'll make clear that the theory is a decidable theory. And I actually have a decision procedure which I'm going to demo for the theory. Okay, so here's how we're going to do it. And I'll just look at a simple case with two atomic sentences, but you know, this would generalize if you have n atomic sentences. So, okay, so this is our standard Boolean stuff. That's in the background here, of course. And now we're going to add another column, which is going to represent a class of probability distributions. And we're going to parameterize these this way. So in general, there'll be 2 to the n of these variables. These are just real variables. Okay, so the a sub I will, we're just going to assume those are on 0, 1. And we're going to assume they add to 1. And the reason we assume that is, well, exactly one of these worlds is the actual world. Okay, so the probability that some world is actual is 1, and that's all this requirement. Remember, this is the probability that this world is actual, this is the probability that that world's actual. Okay, well, some world's actual. So that's why we have, so we just have these 2 constraints on those basic probabilities. And now, everything, we can just define the probabilities in a very simple way. So now, for any sentence in the language P, the probability of P is just the sum. And so for each of these, each of these has a corresponding state or world, which I'll just call S1, S2, S3. So for each state or state description, there's a corresponding basic probability, okay? The probability of P is now just the sum over those states that entail P of the probability of that state, or in other words, it's the sum of the AI such that SI entails P. Okay, a couple things about this. One is, there's a special case for contradictions. The way I'm going to think about this is contradictions get probability 0. Why? Because there are no states that entail a contradiction. That's the empty set of states. So think of that as the empty sum. So I'm just going to take it as given that the probability of a contradiction is 0, because the set of states that entail is empty, and the empty sum is 0. I'm just taking that as a convention. Okay. That's unconditional probability. And now conditional probability, well, it's just Kolmogov's ratio definition. And so now, all the probabilities for any sentences in the language, whether they're conditional or unconditional probabilities, are either going to be sums of real numbers on 0, 1, if they're unconditional probabilities, or if they're conditional, they'll be ratios of sums of real numbers. So what this means is, this theory you can express in the theory of real closed fields. In fact, it's a tiny little fragment of the theory of real closed fields, because for that you have quantifiers for all the real, you don't need all that stuff, but this can definitely be expressed in the theory of real closed fields. And a very weak fragment of it, and Tarski showed that was decidable. And so there's a decision procedure for it, and I'm going to demo that. I have a web-based version of the decision procedure for that. Okay, so let's think about how this works now. Let's just take some simple examples. So I remember I said, here's a theorem of probability calculus. Oh, so let me just, before I get to that, let me just say. So now, here's what we're doing. Here's a way to think about it. We have a probability language, which has probabilistic expression. And then we have the algebraic language. And what we're going to do, the way we're going to deal with this, the way we're going to reason about this is, for every probabilistic expression, there's going to be a corresponding algebraic expression. And for every probabilistic claim, which could either be equations, inequalities, whatever you want, okay, comparisons, there'll be an algebraic counterpart to that claim. So for instance, let's think about, what's the probability of P if and only if Q? Well, by definition, It's the sum of the probabilities of the states that entail the biconditional. Which states entail the biconditional here? This one, where they're both true, and then this one, where they're both false. Okay, so that means over here we're going to have as corresponding, when we translate it, we're going to get A1 plus A2. Make sense? And that's it. That's probability. That's the theory of probability. And by doing it algebraically, it's much more perspicuous. When you do the proofs, it's much clearer why the things are true. Because fundamentally what's going on is algebraic theorems. So when you translate from probability to algebra, if the thing you translate is true for every assignment of numbers that satisfies these constraints. In other words, if this, together with the algebraic stuff you translated, is a theorem of algebra, then the original claim is a theory of probability, a theorem of probability counts. Okay, so example, just to give it an example. I mentioned this theorem. If P entails Q, then the probability P is less than or equal to probability Q. Okay, this is kind of trivial algebraically. Why? Okay, so suppose P entails Q, then something's a contradiction. What's it? So let's do it for just the atomic sense. It doesn't matter, but we'll do it just for the atomic sense. It's not going to matter. It'll hold in general. If it holds, it'll hold, right? So if P entails Q, then something is a contradiction. What's a contradiction?
P true and Q false.
Yeah. What this means, what this assumption basically says, is that the probabilistic import of it is that A2 is equal to 0. That's all that matters. It says more than that, but I'm being a little sloppy here. But okay, it says more than that, but all that matters probabilistically is that entails that A2 is 0. So now, suppose A2 is 0, and now write down this inequality. Probability of P. So now let's translate the probability of P. What's the probability of P by our definition? A1 plus A2. And then what's the probability of Q?
A1 plus A3.
A1 plus A3. And I think everyone can see that if that's 0, then this is a theorem of algebra. The end. That's it. That's why this is a theorem. The axiomatic proof is a lot more complicated and not illuminating at all. I know that. Okay, I mean, what you'd end up doing, the simplest axiomatic proof you give would just recapitulate the algebraic. Or you could do it in a more complicated way. Okay, now, so this gives us just a very general class of models, right? And now for any sense, no matter how complex the language is, doesn't matter how many atomic senses there are, that'll just mean there's more states, 2 to the n states, so 2 to the n variables for n atomic senses. So the number of variables is going to grow exponentially. That's fine. That's how these models work. Let me talk a little bit about visualizing the model. So you'll notice at the bottom of the handout here on page 3, I'm going to use what I call probability tables. So the probability tables are just truth tables with this extra column. But you could also, at least in the simple cases, use a Venn diagram where the circles, where the regions are drawn to scale. So on the bottom of that page, you'll see there's a numerical distribution there. And then I've drawn to scale what I call a probabilistic Venn diagram, where the area of the region in the Venn diagram is proportional to its probability on the distribution. And so the area of the box, of course, is 1, because the box is just a tautology, right, in the Venn diagram. But then if you look at the area of A1, I mean, you can't measure this, but take my word for it, it's drawn to scale. That's going to be approximately 4 over 24 in area. And then S2 is going to be approximately 6 over 24, and so on. So if you like, you can think of probabilities as just areas of regions in a Venn diagram. The problem with that, it's limiting, is because if you have a lot of atomic senses, it gets very hard to draw these things. In fact, it's kind of impossible to draw them to scale in any algorithmic way once you have a lot of atomic senses. So I'm not going to do that. I'm just going to use the tables. So tables, because they're much easier and more general. They always work. You can always specify probability distributions that way. Another thing I want to say before we get to conditional, I want to talk about conditional probability as well. But before we get to that, I want to talk a little bit more about the bounded case for this model as an example model. One thing you'll notice about this model, and I try to do this with all the models in the handout, is they're all rational numbers, and which, by the way, doesn't have to be true, of course, because although this is an algebraic theory, well, you can write down probabilistic constraints that say give you a quadratic formula with an irrational solution, and maybe I'll talk about that. But so you can't always give rational models for any set of constraints. But let's just take, I try whenever I can to give one of these models. And what I like about these models is it's very easy to operationalize the model. So take this model, for instance, here at the bottom, x and y, okay? And imagine an urn with 24 objects. And now imagine that x and y are just properties of the objects in the urn. So maybe x is that the object is a spherical, and not x is that they're cubical. So there's two kinds of objects. They're either shaped like spheres or they're shaped like cubes. And then let's suppose y is that they're white in color, and not y is that they're black. So there's again two kinds of objects in the urn, white or black. And now you could just operationalize this as an urn model. These things are called urn models. Any model that has rational numbers in it is an urn model because you can always get a common denominator and then just be like, oh, there's 24 objects in the urn, and I'm sampling an object at random. And now, the probability of the first state is the probability that it's a white sphere. You see? Because each one's equally probable to be drawn. And so all that matters is the number. And so 4 over 24 gives you the probability. And we can just stipulate that in the urn, 6 out of 24 of them are black spheres. And 3 out of 24 of them are white cubes. And then, of course, 11 out of 24, the remainder are black cubes. You see what's happening? So you can always operationalize these kinds of rational valued models as urn models. And I think that's very helpful to have something in mind. Because one thing you'll notice about this class of models is that it's very rich. We've gone from a class of models that's truth functional, which is essentially finite. Okay, it grows exponentially or something, but it's still finite. To a class of models that now has uncountably many members. There are uncountably many probability distributions, of course, because there are as many as there are real numbers, the way I've defined it. I've just said it's a function to the reals, okay? Now, strictly speaking, the constraints themselves, the algebraic constraints that you could get from equations or inequalities, those can only give you algebraic numbers. Because they're all going to be polynomials, polynomial constraints, okay? If you think about what we're doing here. So the constraints can't entail the existence of a transcendental number. But the class of models is consistent with the sign of transcendental numbers. It has to be, because in physics, for instance, you need those numbers. Sometimes physics tells you that the probability is 1 over pi. That's got to be in there. We've got to be able to access that model, and that's among the models here. Even though the constraints in probability calculus can't entail that those things exist. They can only entail algebraic constraints. But that's fine. We're still going to allow a richer set of values. Any real number. That's important, because in science, sometimes science tells you the probability is 1 over pi. Okay, then it's 1 over pi. And we have to accept that. But for the models I'm going to give, I'm just going to use urn models for the most part. I will, if you like, I should have put this as an exercise. There's a very simple set of constraints just with P and Q that you can write down that entails that some probabilities are irrational. Should I write that down? That's a good exercise. Maybe I'll add that exercise. I think this works, but let me come back to this later. I don't have it off the top of my head, but there's a simple set of three equations that will just determine a quadratic formula, and will give you an irrational number. That can, but okay, so you can actually get irrational numbers just by force because the probability calculus entails existence. You can't get transcendental numbers that way, but still we're going to allow them. But I'm not going to talk about that. I'm just going to give models that are urn models because they're very easy to operationalize. It's hard to operationalize a probability that's irrational. It can't be an urn. No urn's big enough, because that would mean that the probabilities have to be ratios of whole numbers. That won't work. Okay, but let's not fuss with that. Let me talk about conditional probability. Let me say more, because that's really the important concept for us is conditional probability. Okay, you remember, we have this ratio definition. And I want to explain where it comes from. What's the intuition behind it? That's if the probability Q is not zero. Okay, can't be zero. Okay, so I have a nice little diagram here that I like. And so the way to think about what's going on here, when you're conditionalizing on something, the way to think about that is you're supposing indicatively that this is true. You're supposing it to be true in an indicative mood. And so the way we model that here in probability theory is, it's as if you're ruling out, for the sake of argument, all the not P worlds. And so one way to think about that is this. I have a diagram like this on the thing. Suppose you conditionalize on Q. So this represents some probability function where the area is, okay, and so on. But suppose you conditionalize on Q. Well, what you're doing is you're zooming in on the Q circle. Now the Q becomes the box. And now P is just like in here. And so now if you ask, given Q, what's the probability P? What you're basically asking is, what proportion of Q worlds are P worlds? And that's just this. If you think about it, that is just this. Because remember, these give you the proportion of worlds that are P and Q worlds. This gives you of all the worlds. And this gives you the proportion of all the worlds that are Q worlds. When you conditionalize it, it's like you're zooming in on Q. And now that's the new box. So think of this as a new probability function. So this one is the old probability function. And this one's like a new probability star, or probability of Q, is this thing. Where this now, Q has probability 1 on supposition. So now what's the probability of P given Q? Well, it's just the proportion of Q worlds that are P worlds. And that is just given by the ratio of the original. Does that make sense? That's the motivation. That's why we define conditional probability that way. What you're supposing, and supposing is a very strong thing. When you suppose something's true, it's as if you're supposing all the other worlds are ruled out. And so they all get probability 0. And so Q has probability 1. Okay. Now, there's an easy way to prove, and maybe I'll just talk about this real quickly. There's an easy way to prove that this definition gives you a probability function. That it always gives you a probability function. You can do it algebraically. So let's just think about that. So let's just take, and it doesn't matter that we're working with consensus, that'll be general. Anyway, so suppose we start with a probability function. Then suppose we conditionalize that on Q. So now we're going to look at 2 different probability functions. Well, this one we just start with. It's A1, A2, A3, A4. Okay, now, what's this one? Well, by the ratio definition, this is the probability of P and Q. Yes, P and Q given Q, right? What's that? It's the probability of P and Q, which is just P and Q, right? Divided by the probability of Q, okay? And so what is that? A1 over
A1 plus A3.
Exactly. What's this going to be?
Probability of P and not Q. How is it?
Given Q. And that's the probability of P and Q and not Q. Uh-oh. So what's that going to be? It's going to be 0. So is this one by the same argument. Okay? Then this one's going to be what?
Probability of not P and Q given Q, which is also empty.
No. That's the probability of not P and Q divided by the probability of Q. Which is what? A3 divided by A1 plus A3. Oh, guess what? This is a probability distribution by definition. Because if A1 through A4 are between 0 and 1 and add up to 1, then this is between 0 and 1. And this is between 0 and 1. And these are 0, so they add up to 1. The end. So that's a proof that conditional probability really is a probability. And it's very simple when you do it algebraically. To do this axiomatically is a whole rigmarole. Who cares? This is much more explanatory about what's going on. This just shows that whenever you conditionalize, you're getting, if you start with a probability function, you end up with a probability function. And that's important, because if you didn't, why would you call it conditional probability? It has to be a probability in its first argument, and it is. This argument is fully general. It shows that it's always a probability. So the algebraic method is nice. It gives you very simple ways of proving basic things about probability. Okay, so, yeah.
So you're holding Q fixed, and you're varying what you reason adopt, right?
Yeah, well.
Yeah.
Yep. The states are the things that receive basic probability.
But if you do it the other way around, then it's not a probability function anymore.
I don't know what you mean the other way around.
If you fix what comes before, and you vary what you're conditionalizing on.
Right, but that wouldn't be appropriate here, because remember, the things that receive probabilities in the first instance are the states. That's what gives you the unconditional probability distribution. It's the assignments to the states. So now what matters is, do the states, when you conditionalize on Q, do the states get probability such that that is a probability? Yes, that's right.
So the other way around, is it a likelihood function?
We'll come back to that later. Let's not jump ahead. We're going to talk about likelihoods later, but for now, let's leave it. This just makes sense, right? So far, okay. All right, good. So now let's talk a little bit about how we use this algebraic method more generally. It's a very powerful method, and as I said, it's a decision procedure. It's actually, it gives you a decision procedure, and that's because high school algebra is decidable. So that's kind of nice, but let's do one example here, and I think I have this handout. Where is it? Yes, it's exercise 4. But not yet. Before we get to that, so let me talk about the algebraic method that we're going to be using. We're always going to use this method. That's a very simple method. Step 1, translate the set of constraints, probabilistic constraints, whatever they are. They can be any constraints you want that involve equations or inequalities, into algebra. And then the second thing we're going to do is either we'll be working with a given numerical distribution. So either we're just going to plug and chug. That is to say, from a given numerical distribution. That's just plugging in numerical values and then calculating. That's easy. Or we'll reason generally. We'll reason algebraically. Treating the AI as generic variables. Generic real variables. Satisfying the basic constraints. They add up to 1, which means 0. And so you'll notice, these are just things in high school algebra. You're either just calculating values, or you're reasoning generally about a set of equations or inequalities or whatever. And that's high school algebra. That's a decidable theory, thanks to Tarski. Yes, Tarski in the 20s, he was teaching in Poland, and he thought to himself, I'm teaching these students algebra, and there ought to be a more general way to do this, because it was like, he had certain theorems about the existence of roots and stuff like that. He's like, it should just be a more general method, and then he just figured out that the whole theory is decidable. Now, the method that he gave was terrible. Its complexity is not bounded by any tower of exponentials. It's not a good method. By the 1970s, his student Collins came up with the optimal solution, which is still bad. It's exponential in the number of real variables, but that turns out to be the best you can do. So the decision procedure that I'll show you is using that Collins decision procedure. It's exponential, but amazingly, with today's computers and today's algorithms, it solves some really hard problems with it. It's pretty fun. Okay. So, and on Friday we'll talk about that. I'm not going to do anything hard, but on Friday I'll do some hard ones. Some open problems that we solved, actually, in probability. Okay, so that's the algebraic method. Now let's take an example. We already saw one example. Let's take another example. And yeah, maybe we'll just do exercise. Maybe we'll just do the interesting exercise. Here's the theorem of probability calculus. The probability of the conditional is never less than the conditional probability of its consequent given its antecedent. That's going to be important later when we talk about inductive logic. This is an important theorem. We'll talk about it later. How would we prove this using the algebraic method? Well, it's pretty straightforward to do. Let's do this over here. So remember, just to remind you. Okay, so what we have to do is translate both sides. The probability of P arrow Q. Well, that's just the probability of either not P or Q. So what is that? There was only one case where the conditional is false. So we can think of this, if we to be clever, it's 1 minus. But another way to write that is just A1 plus A3 plus A4, because they have to add up to 1. Right? That's one of our constraints. But I'm going to make it easy and just say, but that just follows trivially. The fact that they add up to 1 means that these are expressed the same, always expressed the same value. Does that make sense? Okay. That's the left-hand side. Right-hand side is the probability of Q given P. And so that's a ratio. We've already seen it. It's A1 over A1 plus A2. So now this problem reduces to showing the following thing, that given our constraints, this is a theorem of algebra. And I won't dwell on this too much, but let's cross multiply. We can do that because this has to be greater than 0. So that's not going to change anything. So we get this. Okay, well, let's see. A1 minus A1 A2 plus A2 minus A2 squared minus A1 greater than or equal to 0. Okay. Anyone see how should we proceed here? Oh. Factor out A2. Let's see. Factor out A2, it's A1 plus 1 minus A2. Oh, wait a minute. This has to be non-negative. This has to be non-negative. And this has to be non-negative by our assumptions, so therefore that whole thing is non-negative. Yeah. Axiomatically, that proves a lot uglier. Kolmogorow's way, much uglier. It's just an elementary fact about high school. That's what all the facts of the probability calculus are. Once you realize it's just this decidable theory expressible in high school algebra. Yeah.
What are the connections between this model and SAT problem?
Yeah, I'm going to talk about that, especially on Friday. But I'm going to demo.
Because this seems to be completely connected.
Yeah, this is decidable. This is what shows you that it's a decidable theory. Because you can always translate any probabilistic claim into a corresponding algebraic claim. And you can always determine whether something's a theorem of algebra because that's decidable as Tarski showed. And therefore, by translation back, you know whether it's a theorem of probability. Does that make sense? That's all this is. That's what probability calculus is. So that's an example, a nice example of a theorem that we're going to use later when we get to inductive logic. But on the handout before that, I have some non-theorems. It's also important that some things are non-theorems. And you'll notice at the bottom of page 4, I have a very simple model, again an ERN model with 16 objects this time. And you might ask, how did I find this model? So I wanted a model in which 3 is false, 4 is false, and 5 is false, because I want to show that none of those are theorems. To show something is a non-theorem of probability calculus, you just need an assignment of values to the variables that makes the claim false. Oh, now here it'd be great if I could. Do you think we can get it to work? Because I haven't. Or we could do it on Friday, but let's try it. It would be nice if we could do it. Because this is very cool. We just have an alpha version of this thing now. Let's see if we can make it work. Let's see if we can make it work. Maybe we can.
Thank you.
Hopefully we get this to work. This would be cool. This is very cool. My student and I just finally finished it. It only became possible in the past year or two to do this because the decision procedures are really complicated, and you can finally run this a program called Z3, which we'll talk more about on Friday. That's a general thing that encodes a lot of decision procedures for different theories. And you can now run Z3 in a browser in the background. You just load it into the browser so you can run this algorithm. Let's see if it finds me. HTML. Okay. Good. So can I go back to the board? This is such a production. Sorry about that. Yeah, let's go back to the board. How am I doing on time?
You have 7 minutes.
Perfect.
Or just in the
And we'll do a lot more of the theorem proving for probability on Friday, but because there's some really cool stuff you can do with that program. And you don't need mathematics anymore. Just get your browser and start calculating probabilities and start proving theorems. Okay. That's the algebraic method. That's the best way to think about probability. It really reveals that it's a decidable theory. So this is one reason why I don't mind calling what I'm presenting a theory of inductive logic, you see. Because the theory is decidable. What more could you want from the logic than decidability? This is still logic, I say. It's just probability, but it's logic because it's a decidable theory. Okay, one more thing. Bayes theorem. This is going to come up later. So let's talk. I just want to mention Bayes theorem and some notation and some terminology about Bayes theorem. Here's one version of Bayes theorem that is the one we're going to use. So here we have two propositions, E and H. And the reason we use E and H here is because we're thinking of a hypothesis and evidence, something that's putative evidence for it. Okay, that's why. But it could just be P and Q. Okay, so it's very easy to see why this is a theorem. You don't need the algebra. You don't have to translate stuff. Just use the definition of conditional probability. Okay, let's just use the definition of conditional probability over here. And let's see what we get. Well, the probability of E given H is the probability of E and H divided by the probability of H. Then we're multiplying that by the probability of H. And then the same thing happens here. Apply the ratio definition. Similar thing happens with this term. And now you just cancel. Just to remind you of the algebraic definition here, it's relevant. So what we have is A1 over A1 plus A2. That's why Bayes theorem is. It's just very simple. You apply the definition of conditional probability, do some cancellation, and then you realize, oh, this is just A1 over A1 plus A2. But that's what this is by definition. So that's easy. Again, algebraic, way to go. Very perspicuous. That's the way to think about this. This theorem is very important. We're going to talk a lot about it. I just want to say a couple things. One is terminology. Very important terminology that we're going to be using later. Probability of H given E is called the posterior of H relative to E. Posterior. Probability of H unconditionally is called the prior, or the base rate. We'll talk about base rates of H. It's just the unconditional probability of H. We call it the prior of the base rate. Probability of E given H is called the likelihood of H. This came up before. Likelihood of H relative to E. And the probability of E given not H. Well, there's different names for this. You can think of it as the likelihood of not H. It's also sometimes called the catch-all likelihood. Again, relative to E. So I'll just call it the catch-all usually. And so what Bayes' theorem tells you is that the posterior is determined by three things: the prior, the likelihood, and the catch-all. And it tells you specifically what function of those three things it's a function of. Now, of course, you can think of this algebraically. Think about the algebraic space. It actually only has 3 degrees of freedom because this is 1 minus. So there are 3 unknowns here, right? And basically, you're specifying 3 unknowns here, and that's going to determine uniquely a probability distribution. When you specify these 3 things, that's everything, it turns out. Because it's 3 equations and 3 unknowns. And you're done. So you don't just get the posterior from these 3 things, you get the entire distribution from those 3 things. So you get the probability of anything, given anything. So basically, Bayes' theorem is just a special case of a more general thing that says if you specify these 3 things, you've uniquely specified a probability distribution over UNH, over the algebra defined by UNH. Okay, I think I'm done. Thank you very much.
Okay, so maybe you have some questions. We can extend a little bit because of the technical problem that we have until 12:20, maybe.
I have a question concerning
Yeah.
closed fields, right?
Yeah.
It's a more technical question. The fact of using real closed fields, firstly because it helps in decidability, etc. But is this a choice or a consequence?
This is a consequence because when you look at the algebraic translation, it's actually just a tiny little fragment of the theory of real closed fields. It's really just what you should call high school algebra, which just involves adding numbers, dividing numbers, and taking equations or inequalities among those things. That's just high school algebra. And high school algebra is just a tiny fragment, because the theory of real closed fields allows you to quantify arbitrarily over the variable. We don't need to do that. All we really want to know is, does there exist an A1, A2, and A3 such that certain constraints are satisfied? So it's a pure existential problem in the theory of real closed fields. So it's really just the existential fragment of the theory of real closed fields, and even a tiny fragment of that, because it's just adding numbers and taking your shapes.
But then the question is this sufficient? Or should we go for, say, complex number or something?
Well, it's sufficient for probability calculus. It's sound and complete with respect to Kolmogor's axioms. Oh yeah, that's an easy thing to do. That's very simple to verify. All you have to do is prove Kolmogor's 3 axioms. They're easy. All the probabilities have to be between greater than or equal to 0. That's obvious. It's sums of the numbers that are greater than or equal to 0.
You prove that it covers
Yep.
and vice versa?
And vice versa, yes, that's right. Yep, it's equivalent. What I presented is equivalent to Kolmogor's. It's just a more perspicuous way. It's a semantic way. You understand what really the meaning is. What's fundamental are the probabilities of the states of the possible worlds. Everything else is determined by that, by either adding up things or dividing sums of things. Yep. It's just a more perspicuous way of presenting what's going on in the finite version of Kolmogor's theory.
So, any more questions? Nathan?
I have a quick question related to the first part of your presentation. I was wondering how to reconcile, how to square this view of science as at the core being about modeling, which necessarily involves idealization, which strictly speaking are falsehoods, with the claim that we have knowledge about scientific things. Does that mean that we know false things?
No. I think we know a lot of stuff. I think that's fine. We know a lot of things. What we take ourselves to know at any given time is, of course, fallible and revisable. So let's just take cosmology. And this is an idealization itself, because of course people know there's anomalies in cosmology. They don't fool themselves to thinking that there's no anomalies. Okay, well, let's set that aside. Let's suppose we think general relativity is true as a description of space and time. That's fine. We may believe that. I think it's fine to believe that. I think it's fine to take yourself to know that. But of course, that's fallible, right? You may not know it because maybe it turns out that it's false. Okay? But I don't think there's any good reason right now to reject it. I mean, are there reasons to be uncertain? Sure, but all of our knowledge is uncertain. I mean, except logic and mathematics. All of our knowledge is uncertain, so that's okay. That doesn't matter. You can't, infallibility can't be required for knowing, because then you'd be a skeptic. We're not skeptics. We do think we know. Of course, we might be wrong, and well, then we'll revise our beliefs accordingly and accept the best theory best overall theory we have. Modeling is central to what we do in science on a case-by-case basis. It's just how science functions. It's how it operates. I'll come back to this at the end when we talk about the reasoning fallacies and the psychological experiments that are run. That's a good example to think about how science works. But yeah, in general, we perform experiments. We design and perform experiments. And then we interpret the evidence they produce. And what I'm going to give you is basically a theory that allows you to understand the significance of evidence that's produced. So nothing I'm going to say officially really depends on us knowing that the theories are true. But do we know things? Yeah, we know a lot of things. For instance, I think we know there are electrons. Okay. Could we revise that belief later? Sure. We can revise anything. That's not a reason to think you don't know. Right? And you don't want to be an infallibilist because then you'll be a skeptic. So I think we know a lot of things. I think we know there are electrons. I think I think we know that the moon is less massive than the sun. We know a lot of stuff. Okay. That's compatible with thinking that what's fundamental to science is the exercise of modeling. Those are compatible. You don't have to be committed to the truth of anything. You don't have to think, and many scientists aren't. Many scientists say, okay, we're doing the modeling, and that's all we're doing, and I'm not going to make any commitments beyond that. That's fine if you want to do that. I'm a realist, so I think there's a fact of the matter, and I think we know a lot of stuff, like I said, and so I wouldn't necessarily think I know all the aspects of all the theories, but some of them, sure. There's a lot of consequences of theories, like that the moon is less massive than the sun, which are just true, you know. Okay. And then there's more subtle things that, okay, maybe we're not sure whether we know them or not, or we're not confident we know. That's all compatible with thinking that what's fundamental is this practice of modeling. I think that's all compatible. Yeah. Oh, yeah. Professor.
I love your, app as a theorem prover, and I like it even more as a counterexample constructor.
Yeah.
Do you have a readable description of how the algorithm works and source code, this kind of stuff?
Oh, yeah. It's all going to open source. We're currently in alpha version, but it's just going to be open source, and anyone can play with it. But all it's really doing is, right now, we're going to make it a little bit more sophisticated. All it's doing right now is taking your inputs, translating them into high school algebra, and then feeding them to the decision procedure, which specifically we're using Z3. Z3 is like the industrial strength theorem prover and decision procedure that everyone uses. It's by Microsoft, so it's always updated. It's very powerful. It's really good at these existential problems in the reals. And so we're just feeding to that, and then whatever it gives out, we're just formatting. And then once you have a model, now it's just calculated. You just want to plug and chug. Now you just substitute values. Calculate. That part's easy.
The engine behind it is
Z3. And I'll talk more about that on Friday, because that's into the theorem proving stuff. And I'll talk more about Z3 on Friday. The algorithm, Collins's algorithm, which is called cylindric algebraic decomposition, is a very, very sophisticated algorithm. I had a student who implemented it in Haskell when I was back at Berkeley, and it was, there's a whole book on the best ways to implement. There's like a 600-page book. It's a very complicated algorithm, so it wouldn't be easy to, but there's a really nice informal description of it, which I love. It's by Solomon Pfefferman, and it's in the book Tarski, Love and Logic. I don't know if you know this book. It's a biography of Alfred Tarski that the Pfeffermans are fantastic. Tarski, Love and Logic. In that book, Pfefferman, so Anita Pfefferman was a biographer, and so she does all the kind of salacious bits, all the fun stories about Tarski and his womanizing and all that. And then Saul Pfefferman, I don't know if you know who that, do you guys know who Saul Pfefferman was? He was an amazing man. This is like a grandfather to me when I was in the Bay Area. Amazing magician and wonderful person. He has these interludes, logical interludes throughout the book, and one of them is about the history of the algorithms of the decision procedure for algebra. So I would recommend that. It's super readable. I mean, it doesn't go through all the details, but it gives you the basic gist of how these algorithms work. They're really complicated, but this gives you a nice sense of how they work. So yeah, I would recommend this. Pfefferman's interlude on love and logic. Love and logic. So she did the love part, and he did the logic part. It's a wonderful book. So you have all these fun stories, and then there's a logical interlude about one of Tarski's contributions, and then it just goes on. It's fantastic. Great book, really good book. So, and that's the best. That's the most accessible introduction that I know. And then if you want to get more into it, and I'll talk more about this on Friday, then the thing to look at is Harrison's book. And I'll make this stuff available. I'll just make all this stuff available. I'll make a Dropbox thing. We'll just put it. Harrison has a book, a handbook of automated reasoning. I think that's what it's called, but I'll put it in this Dropbox. And that is like the Bible. That Harrison's book is amazing because what he does is he goes through all the classic algorithms, both the theorem provers, the model finders, and the decision procedures for basically all the famous theories. And he, starting from scratch, implements all of them in Haskell as you go through the book. It's amazing. So that's, if you really want to do it, he just does it. So you just, by the end of that book, you have all the code for all the theorem provers and all the model finders. It's insane. It's so beautiful. Yeah, that's like the best. But I would start with Pfefferman just to give you a sense of how it works. And then you can, if you really want to dig in, Harrison has everything. It has all the theorem proving stuff that I'm going to talk about. It has all the decision procedure stuff. And he actually implements it all. I think it's in Haskell or something crazy. I don't know, some weird language that I don't use. But if you want, you could actually do that. So those are the two. But I'll put a bunch of stuff together for Friday, and I'll have a whole set of PDFs. There's some really good resources out there. But yeah, that's all we're doing. We're just feeding it to Z3. Now, my version in Mathematica is much more complicated. The version in Mathematica does a lot of other stuff. So the version I have in Mathematica is very sophisticated. So what it does is, it takes the constraints, and then the first thing it does is, if there's any equational constraints, it solves that to eliminate some real variables, because this algorithm is exponential in the number of real variables. So if you can even eliminate one, it's a huge speed up. So I go to a smaller manifold with those equations are satisfied. And then, before I even send it to the decision procedure, I first have a random search algorithm, which is actually really fast. It's linear in the number of real variables. And that usually finds a model if there is one. Of course, not always, because sometimes there's irrational values, and this is numerical, so it won't. But if there's a rational value model, it almost always finds one. Real quick, because it's linear in the number. And then only if that, after a bunch of tries of the random search, only then does it feed it into the decision procedure. The problem right now, and the reason I'm so glad we did this is, one, Mathematica is amazing, but the problem with it is it implements such a general version of this algorithm, the cylindric algebraic decomposition. It's too general. So on the existential part, it's too slow. Whereas the Z3 is just the existential, so it's optimized for that problem. And so it just kills these simple, just existential instances. It kills them. And that's why I've been waiting to try to do this in Z3. We can finally run it in the browser now. Oh, wait, I should tell you, maybe on Friday. My student, Quasi, he's the guy who did it. And I think I mentioned him in the footnote. Yes. Quasi was a student of mine in my advanced logic courses, and then he graduated some years ago. And while he was a student in my advanced logic course, he rewrote, I had this old bad software for learning how to do natural deduction proofs in first order logic. He rewrote it all as this beautiful web-based thing that you can just pull up. So now that's what I use in my advanced logic course for doing proofs. And then last year I said, I think we can run Z3 in the browser now. And so in the last 2 months, this just took him 2 months. And I'm paying him $20 an hour. He makes $400 an hour, but he doesn't care. He's interested in pedagogical software. So I wish he was here because he's so great. He's recording a demo. So what's going to happen is when this goes public, which will be in the next month, I'm going to put up a website where there'll be a video demo of Quasi demoing all the features and showing you how to use it. And okay, that's coming. So but for now, we don't have that yet. But I wanted to at least show you. We do have an alpha version. It works pretty well. There's still some bugs. And I'm hoping you guys will use it so you can give us feedback on other bugs. I'm sure there's some other edge cases and stuff we haven't figured out. But yeah, this is Quasi. my student. He's such a good programmer, and he loves logic and helping to teach people stuff. So I'm using this mainly for pedagogy. I think it's so important for teaching. The ability, so we have truth table generators, and I give the students that. That's really helpful. Like, you can just play with the truth table generator and learn what tautologies are and so on. Now we have a probability table generator. You do the same thing for probability calculus. It's amazing. Now students are going to learn it much better, for sure. So I'm super excited about this. Anyway, I'll talk about it later. Sorry, that was a very long answer.
Yeah, now we have only 2 more questions, quick, because we have to lunch and be back at 2. So we'll start with Guilherme.
Sure. Isn't just the existential fragment from the cylindrical algebraic decomposition an overkill already? Because I mean, you're dealing with a very, very small sub-fragment of the existential problem in cylindrical algebraic.
Yes, that's right.
Can't you have something else? Because I'm thinking Z3 can't write you proofs for the cylindrical algebraic decomposition yet.
Right.
I know there are people working on that, including Daniel Barbosa here in Brazil.
Oh, great.
Working on that. But I know you can't write a readable proof.
Right, that's right.
So maybe can't you have something simpler? I don't have a suggestion.
Well,
to
let's talk more on Friday.
Okay.
If you can make it on Friday, that'd be great, because you obviously have a lot of experience with these things. Here's one thing I will say. My Mathematica package has tons of other stuff. One thing it has is a function called PR reduce, which gives necessary and sufficient conditions for any set of constraints. That's computationally hard. Okay, this is, and NZ3 can't do that. See, so Mathematica has the full decision procedure for the entire theory, which means it can take any set of constraints and reduce it to a quantifier-free, necessary and sufficient set of algebraic conditions for any set of algebraic constraints. And that's cool. I also have another function called PR range, which takes a probabilistic quantity, a term, and a set of constraints, and tells you what the bounds, because you can solve for max and min. That's all just decidable. So I have PR range, I have PR reduce, I have all the PR simplify, I have all this other stuff that's under the hood in PR. So if you're interested, we can talk about it. There's a lot of stuff that Mathematica can do that, of course, Z3 can't do. So it can't produce proofs, but it can give you necessary and sufficient conditions rather than just giving you a model. Very nice. Yeah, and in fact, I published a paper some years ago where I was able to show that a set of premises was much stronger than people thought by just using PR reduce, and then it gave this extremely simple set of conditions so people didn't realize how strong the assumptions were. And then I recently realized they're even stronger. They're actually incompatible with but you just have to set up the problem the right way to see that there's actually no models. So yeah, tools like this are super valuable because it's very hard to think about problems. Probabilistic constraints are very difficult intuitively to see whether they're satisfiable, how they'd be satisfiable, what the models look like, but you can now just characterize them completely. That's why I like doing it this way. Much better than axiomatic reasoning. That's not going to be very helpful here, right? Anyway, we should talk more about it because obviously you have a lot of experience with this. That would be helpful. And I'm interested in improving the tools, right? So I would like feedback like that, of course. Thank you.
So final question.
Yes.
I want to go back to the logical limitations of
Yeah.
deductive logic.
Yes.
When you were addressing undergeneration cases, you mentioned
Yeah.
this inferential schema that is called activity of knowledge.
Yeah.
From knowing that P, you can infer B.
Yes.
Okay, I got that schema is not valid in propositional logic.
That's right.
But you also claim that model logic wants.
Well, Walter asked this question. Now, of course, this goes back originally to what we were saying. Now, of course, if you enrich the class of models, you can do all kinds of stuff. Of course, remember, it's always relative to a class of models what you're able to explain, right? So my claim was only truth functional logic can't do that. Yes, you could add a sentential operator for knowledge or something like that, and then add an axiom, the T axiom. And that would allow you to capture that argument. And that's fine, and that's great. I have nothing against that. However, I don't think in general that's the probative strategy here, because remember, you have to remember what the explicandum is. What I'm interested in is, when is a proposition for a person under a certain state of uncertainty a reason to believe another proposition. And I just don't think all the fiddling you want to do with deductive logic isn't going to help, because most of the arguments aren't even deductive at all. Yeah. We're going to come to that. We're going to come to that. The interesting arguments in science right now aren't deductive at all. And so there's no deductive logic that would be sufficient to capture them. They're simply non-deductive. So it would just be a category. And I think that's a fool's errand if you think, oh, I'm just going to make deductive logic more and more sophisticated. So I can. Now, there are people who thought you could do that. Karl Popper thought there was no such thing as amplitude reasoning. It was all deduction. This is wrong, and for reasons that I'll explain later. This can't be right. Yeah. A lot of people used to think that was right. In a certain rationalist tradition, which Popper was a part of, he thought you could reduce all reasoning to deductive reasoning. This is not true. In fact, I think we have a lot of evidence now that a lot of knowledge we have and a lot of things we do are because we're performing lots of sophisticated statistical and non-deductive inferences. I think the large language model is basically the way. Do all the deduction you want, and it ain't going to help. I mean, it'll help with these little examples, but you see, there's a much bigger story here, which is what we want is a general theory of when one proposition is a reason to believe another for an agent in a certain kind of state of uncertainty. And deductive logic just isn't going to give you that. It'll give you some of it, yeah, for the good, non-trivial deductive arguments, or the ones you can formalize as a deduction. Yeah. But that's just a tiny fraction of the arguments in science. Yeah. So I have nothing against doing that. I just don't think that's a global strategy that's going to. It'll get some of the cases, but it's not going to get all the cases. No matter how much you try. I mean, I know, Popper notwithstanding, but I just think he was wrong about it.
Okay, so
thank you so much. Thank you very much.
Do we know